Okay. All right. So, guys, first of all, try not to unmute while I'm teaching something. Okay, if you guys unmute and you guys talk, then that will just end up distracting everybody, and uh, that would also mess with the recording. So, if you guys can stay muted, and any queries that you have, just mention me, ping me in the chat box. Okay, if you have any question at any time, I don't mind your questions. I mind that you guys unmute and then speak in the chat because that disturbs everybody, including the recording. So if you guys have any questions, just ping me in the chat. I will get to you. Okay, so don't worry about that. And yeah, okay. So about the session, I've started the recording and everything. We're gonna begin. About the session, uh, we're going to cover, or at least try to cover, chapter 1, 2, 3 today. That's gonna be done today, inshallah. And chapter 4, we're also gonna try to cover that today, but I'm unsure if we'll be able to do that because of the restricted time. But we're gonna try to basically cover like the first 4 chapters today. Uh, Stream is full. Wait, are you guys able to look at my stream, all of you? How long is this?
Yes.
Guys, if you're unable to look at my screen, then message. If you're able to look at my screen, then don't message. If you're unable to, then message, okay? If you're unable to, only then message. Are you guys unable to look at my screen? Can't watch. Does it tell you guys the same thing that Rod sent? Does it say it's full? Oh, I think we will have to move to stage. Shit. I think we will have to move to stage. We will have to. Holy cow. We're at 50 viewers. Yeah, we'll have to move to stage. We'll have to move to stage. Yeah, we'll need to move to stage. Okay, we'll move to stage. Somebody move us to stage. Move to stage. Move to stage. Wait. I was generally not expecting a lot of people to
Potato
show.
A2 said Ateeb A stage is necessary.
Let's move. Alright, we're gonna move to stage, guys. We're gonna move to stage. We're gonna move to stage. Oh man. We're gonna move to stage. Kind sir, are you kind? What kind of question is that? You gotta move to stage. Shit. Okay, guys. If you look in your Discord screen, somebody's asking how to join stage. If you look in your Discord screen near the channels, the same voice channels, you know, the off-topic Anon confessions where all these channels are. Just above that, there's this thing called community events. The icon looks like a person. Just click on that. That will take you to stage. I will meet you guys over there. Okay, just go over there. Click on the community events thing. That'll take you guys over there. I'll see you guys over there. Okay, I'll see you guys over there. Let's go. Oh my god. Mama.
And Potato A2 said Ateeb you didn't accept the speaker request.
We are requesting Ateeb. Oh, he joined.
Okay, sorry guys, my Discord crashed. So many people joined all of a sudden. My Discord decided to give up. Okay, so alright, let me just settle up everything. My MacBook is lagging so hard right now. Let me just get my power adapter. Alright, so okay, so as I was saying, we're gonna try to cover the first 4 topics in today's session. Anything that's left, including past papers, we're gonna cover that tomorrow around the same time. I'll let you guys know at the end of today. So,
And Potato A2 said, okay everyone, enjoy the movie and have some popcorn with you to ensure for a smooth experience. Make sure to turn your phone's ringer off during the experience to avoid.
okay, so I'll stream in a sec, just a sec. I'm just fixing my MacBook. It ended up crashing because of the amount of people that suddenly ended up joining. Okay. Alright, so we got 102 people right now. That's insane. I was expecting like 15 or maybe 20. Okay. Alright, so are you guys finally able to see my screen? Okay, so as I was saying, now that we're in the community events chat, guys, if you have any questions, ping me so that I'm able to see you guys. My status is online, so I'll be getting notified every time there's a ping. Don't worry if I don't respond to you. Some text can like flood up with the chat, so just ping me again if I don't respond to you. Right now we're gonna start off with the first chapter, data representation, and we're gonna cover that topic, do some past paper questions, move on to chapter 2. Let's see if we can cover this topic in under an hour. It's a small topic, so yeah, it's gonna be a quick revision marathon, and let's start. Okay, so when we talk about computers, the main thing that you need to know is that each bit, as we call it, it can either be a 1 or a 0, right? So I'll write this down as well. Okay, so each bit can either be a 1 or a 0. Or as we refer to this, we also refer to this as on or off. Okay, so 1 basically means on and 0 basically means off. Now, this sequence of numbers, this sequence of ones and zeros, sequences of ones and zeros, can be used to represent different other numbers and different characters. These things are all called number systems. And in our IGCSE syllabus, we have 3 kinds of number systems. These are the binary, the denary, and the hexadecimal. These are the 3 kinds of number systems that we have at our level. Okay, so in chapter 1, one of the first things actually is to learn how to convert between these 3 different number systems. So let's all start with that. Like I said before, each 1 or 0, it represents a certain on or off stage, right? So for instance, I can say right now the lights in my room, they're on, so I can say the lights are a 1 right now. All right, and if I'm drinking water, I can say that I'm drinking water, I'm wanting the water, something like along the lines of that, right? Okay, so similarly, if I give you guys a scale of, let's just say I give you guys a scale like this, I write down a few numbers on a piece of paper, 32, 16, 8, 4, 2, 1, right? And I tell you guys to represent a number using ones or zeros, okay? And I give you guys a number as well. Let's just say I want you guys to represent a simple number 8, okay? So in order to do this, what we do is we assign a 1 or a 0 to each one of these values, okay? So I'd say that the number 8, it consists of 8 only in this case, okay? And I'll explain how I got to that, okay? So I'll say that the number is basically 0 0 0 0 0 1 0 0 0. Okay, now how I got to this case is that I took the number 8 and I said that it contains 8 only, hence the 1. Okay, or if you have a different number that is like 9, I'll say that it contains an 8 and it contains a 1. Or if you have a different number like 10, I'll say that it contains an 8 and it contains a 2. Alright, so we're basically using ones to signify the number of small numbers in a large number. Okay, you can have it like that. And this number system is called the Denary number system. And we also refer to this as a base 10 number system. Base 10 because there are a possible of 10 values. So there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9, and then lastly there's 0, right? This is why we call it a base 10. Okay, now one thing that you're going to notice is that these values 128, 64, 16, 8, 4, 2, 1, you can use these to make any combination of numbers. Okay, any combination. You can go on and on. Okay, you can say after 128 you can add 256 or 512 and so on and on, and you can make almost anything that is any number within the limit, besides of course the maximum. Okay, so let's just think for a second. What is the maximum possible number that I could make using this? It's gonna be 111, 111, 11, right? In which all the values are all true. Okay, I'm lagging. Okay, tell me when my voice is fine again. Is my voice fine? Okay, so the maximum number that you can represent is obviously going to be 111, 111, 11, right? So what is this number in Denary? It's going to be 255. Okay, you can add the values up. You can add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and you'll see that this equals to 255. This is the maximum value that can be represented by an 8-bit number. Okay, this is the maximum value that can be represented by an 8-bit number. And why am I calling this 8 bits? Because if you look, there's 8 total bits in this number. Okay, 8 different slots. Okay, 8 different slots. Alright, so the Denary number system, it's a base 10 number system. Now let's learn a bit about conversions. Okay, so like I said, you can use ones and zeros to signify if a larger number is made up of a smaller number, right? Simple thing. So if I give you guys a binary value such as 0001, 0001, and I tell you guys that the slot is 128, 64, 32, 16, 8, 4, 2, 1. You guys can plot this out and you guys will see that the numbers, they coincide with, so it is basically 16 plus 1, which is equal to 17. This conversion is simple. Okay, this conversion is simple. All right. Now, another question that might arise is, why are we using 128, 64, 16, 8, 4, 2, 1? So you can imagine binary numbers as kind of like parking slots. Okay, imagine you're in a parking area and there's 8 different parking slots. Right? You're basically assigning a value, which is either 1, 2, 4, 8, 16, 32, etc., to each one of those parking slots. These refer to 2 to the position, to the power of the position. So for instance, on the 0th position, alright, we start from the right and we start from 0. On the 0th position, it's going to be 2 to the power of 0, which is basically equal to 1. On the first position, it's going to be 2 to the power of 1, which is equal to 2. And so on and so forth. Okay, so if I tell you guys to make up a slot for, let's say, 12 bits, right? You guys would go 1, 2, 4. You guys would go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2056. Though you won't need to go through all of this. Okay, you won't need to really learn all these values. All you can do is just write down one number and just multiply it by 2. Okay, you won't be asked to make this long. All right, so that's how you convert from Denary to from binary to Denary, right? You just make a slot, put the binary number there. If it's a 1, you add that. Okay, now the conversion between Denary to binary. All right, so if I give you a binary number such as, let's say, I give you a binary number of 17. How would you end up converting this? All right. How would you end up converting a number like 17 to Denary? So the way to do that, there's two ways that it's usually taught. In the end, both ways are the same, right? Both ways are the same. 2048. Right. Am I lagging? Am I lagging? Okay. So in the end, both ways are just the same. They just differ mathematically. Okay. So the way that I'm talking about is you make the empty slots, right? So 128, 64, 32, 16, 8, 4, 2, 1. Now you want to start on the right side. You want to start on the right side, and you want to subtract the numbers which are less than 17. I'll explain what I mean. So for instance, you have the number 17, right? And you're going to start from the right side. I'll zoom in as well. Also, people who are wondering, the app, it is Obsidian, so don't ping me if that's your question, okay? It's Obsidian. Right, so I'm going to start from the right side. So does 17 comprise of the number 1? So if I subtract 1 from 17, it's still going to be greater than 0. So I'll say yes, it does comprise of 17, and I'll minus that from the original number, which will give me 16. All right, now what's the next number that could that could go in this register, right? So directly I'll see that the 16th register can be used. All right, the 16th register can be used. So I'll say that it contains 16, which is going to be 3 zeros and then 1. Okay, so it's a bit confusing right now, but I'll explain it in a better way. Let's try another number. Okay, let's try the number 72, and let's make the registers again. All right, so this is also referred to as the subtraction method. Okay, this is also referred to as the subtraction method. In my opinion, it's the easiest method, but again, it depends on how good you are with quick maths. So starting from the left side, is 128, okay, easy peasy guys. So you take your number and you start from the left side, and you're thinking, is 72 is 72 greater than 128? All right, since it's not greater than 128, we're gonna add a 0, okay, because this basically means that 128 is not comprising of 72 is not comprising of 128. Then you go over to the next number. Is 64 less than 72? All right, it is less than 72, so you write a 1 and you subtract 64 from there. Okay, so then you're left with 8. Now you're gonna go over to the next register. It's the 32. Is 32 less than 8? It isn't, so we're gonna write a 0. Is 16 less than 8? It isn't, we're gonna write a 0. Is 8 less than or equal to 8? Remember, it's less than or equal to. My bad for saying less than. It's less than or equal to. Is 8 less than or equal to 8? It is equal to 8, so we're gonna write a 1. Now we're gonna be left with 0, and then that automatically just cancels out because neither of these numbers can be less than or equal to 0, so we just write 3 zeros. That's the first method of converting a denary to a binary. Okay, that's the first method of converting a denary to binary. Let's take another number. Let's take a larger number this time. Okay, let's go with 726. Okay, I doubt this kind of a question can come in your exam. Okay, that's probably not going to come, but let's just assume that we're taking a large number. Okay, just to grasp the concept. So let's just say that I want this in the 12-bit form. All right, so it looks something like xxxx xxxxxxxx, where x is either 0 or 1, right? Okay, so let's say in the 12 bits, okay, there's 12 different positions. So these are 2048, 1024, 512, 256, 128, 64, 32, 421. This is a gigantic number. Okay, you guys probably won't need to worry about this, but it's a gigantic number. We're just trying to understand the concept. So you start from the left. Is 2048 less than or equal to 726? It isn't, so we're gonna write a 0. Then 1024, is this less than or equal to 726? It isn't, so we're gonna write another 0. Same for 512. Now 512 is less than 712, so we're gonna write a 1, and then we're gonna subtract 512 from 726, which will give us that gives us 214. All right, so now we have 214. Is 214 less than is 256 less than 214? It isn't, so we're gonna write a 0. 128, it is, so we're gonna write a 1, and then we're gonna subtract it. Okay, so we're left with 214 minus 128. We're left with 86. All right, now is 64 less than 86? It is, so we're gonna write another 1 minus 64, and you're left with I believe 22. And now, is 32 less than 22? It isn't, so we're gonna write a 0. I forgot an 8. I forgot a 16 and an 8 here. All right, now 16, is that less than? It is, so we're gonna write a 16, and this in terms end up being 6. So, and we're gonna write a 1 over here. All right, I hope you guys are getting what I'm saying so far. Okay. Next we have the value of 8. Is 8 less than or equal to 6? It isn't, so we're gonna write a 0. Next we have 4. That is, so we're gonna write a 4, and then we're gonna move on to the next one, which is going to be 2. It is, so 2 is equal to 0. All right, and that's it. That's how you solve questions from Denary to binary. Okay, so the final number for this is going to be this, and you can reverse engineer this as well. Okay, so for instance, you're going to say that this is the 2048 value, right? It's 0, so we're going to skip this. This is the 1024 value, we're going to skip this. This is the 512 value, so we're going to say 512 plus 256. It's a 0, we're going to skip. Okay, next you have 128. We're going to do this. Okay, I'm just going to write 128. All right, next you have 64, which is a 1, so I'm going to do 64 plus next you have 32, then you have 16, so 16 plus, and then you have 4 plus 2. All right, 4 plus 2. You'll also see this corresponds with the numbers that we subtracted. Okay, so this would in terms give us the answer of 64 plus 16 plus 4 plus 2, 726. Now, what I want you guys to remember is that they're probably not gonna ask you for these kinds of questions, because you're not gonna be allowed a calculator. Okay, they're never gonna ask you for having this large of a number, because you're not gonna have a calculator. All right, I just do this to help you guys understand the concept. Okay, I suggest working with large values a bit, so that when you go in the paper, you're confident in your math skills, and you're confident in your conversion skills. All right, that's why I chose a large number. Else you don't need to know a large number. So this is basically and one more method. All right, I almost forgot. The other method is basically called the LCM method. I don't exactly remember this, but I'll try my best. Okay, so imagine you have a number such as 400, or actually let's start off with a smaller number. Let's just say you have a number such as 67. All right, 67 is your number. This method, I don't recommend this method because it's a bit complicated. Okay, plus you have the subtraction method. Subtraction method's the Pookie method, I guess, so that's what you should go with. But either way, this is the LCM method. What you do now is you start off with the LCM method. You basically divide this by 2. Okay, so dividing 67 by 2 gives you the quotient of 33 and a remainder of 1. How did we get to this? Calculator division. If you divide 67 by 2 and then you convert that to a whole number, you'll get like 1 as the remainder, and then 33 as the you'll get 33 as the remainder and 1 as a, you get what I mean. Okay, you get what I mean. All right, so this method absolutely sucks. I don't recommend going for this, but still, it's a thing. Then you divide 33 by 2, you're left with 16 remainder 1. All right, you're left with 16 remainder 1. Then you divide 16 by 2, you're left with 8 remainder 0. Divide that by 2, you're left with 4 remainder 0. Divide that by 2, you're left with 2 remainder 0. Divide that by 2, you're left with 1 remainder 0. Alright? Or if you want to notice a pattern here, you could just, like, if it's an odd number, subtract 1 divided by 2 and then just put 1 as the remainder, which is what I did. Okay? Now what you want to do is you want to go from the bottom to the top. Okay? So this is going to end up being 1, and then you see there's a 0 over there, then another 0, and then another 0, and then another 0, and then a 1 and a 1. That is going to be your binary value, and mostly you'll need to answer the questions in 8-bit form. So in order to make this 8 bits, I'm just going to add 1 0 to the left. That's your final answer. Okay, and you can cross-reference this as well. This is going to be 128 position, that's a 0, so we're just going to do a 64 plus 32 0, 16 0, 8 0, 4 0, 2, yes, 2 plus 1, yes. So this ends up being 67. Alright, that's the second method. I really don't suggest using this method. Okay, it's a trash method. I hate this method. I recommend using the first method, the the subtraction method, but this is also like a possibility if you just want to double check your answers or whatever, right? So that is the conversions between denary and binary. Okay, now let's talk about the conversions between hexadecimal and binary. Okay, so binary and hex. So to understand these conversions, what you want to do first is you want to understand the concept of how this whole thing works. Okay, so what is hexadecimal? Hexadecimal is a base 16 system. What that means is that there is a possibility of 16 different characters. Okay, so there is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have capital A, capital B, capital C, capital D, capital E, capital F. These are your possible values. Okay, these are your possible values. Now in hexadecimal you can represent this in a similar way to binary. Okay, so if I give you a 4-bit register, okay, how does that look like? That would look like a 8421, right? If I give you a 4-bit register, okay, and I tell you that what do you say, that this is a 0, represent each of these in binary, what will you do? It's simple. 0 in binary, that would be 0 0 0 0 1 0 0 0 1. I'll just do this for the rest of them. Okay, if you guys have any questions, just let me know. So this is what it will look like all the way up to I think 7. That's 7. This is 8. So till 9, pretty easy. After 9, what you want to do is you want to represent these values as numbers. Okay, so you can imagine A as 10, B as 11, C as 12, D as 13, E as 14, and F as 15. So this becomes 1010, 1011, 1100, 1101, 1110, and 1111. Alright, so if you also notice the pattern here, I'm just adding 1 to each one of these. So yes, pretty simple. You won't need to make the table. It's if you can convert between binary and hexadecimal just by looking at it. For instance, if I were to give you a binary number such as 00001100101100 or 1101, the first step to convert this binary number from binary to hexadecimal is to, starting on the right side, what you want to do is you want to go 4 places and then you want to add a split. Alright, then you want to go 4 more places and then you want to add a split. Alright, so now you have 3 bits or 3 groups of 4 bits. Alright, now what you want to do is one by one you want to convert these to hexadecimal. Now the simplest way to do that is just in your mind imagine what this would be in denary and then just reference that as hexadecimal. So like for instance 0000, this would be 0 in denary, so we're going to put this as 0 in hexadecimal. Then 1100, this would be 8 plus 4, so this would end up being 8 plus 4, which is 12. Now remember, we don't have anything above 9 in hexadecimal, so we're gonna convert this to hexadecimal. So remember, A is 10, B is 11, C is 12, so this means that this is gonna be C. Alright, this is gonna be C. And then you have 8, this is 8 plus 4 plus 1, so 13, and 13 is just D, so the final answer is 0CD. Alright, simple. That's how you convert from binary to hexadecimal. Now in order to convert from hexadecimal to binary, you just reverse this process. So if I give you a number like ABC, or let's make it even bigger, 1 2, ABC 1 2, you're gonna start from the left or the right, it's your own choice. I prefer starting from the left because you know it's simpler that way. So A in denary, what would A be? What value do you use to represent A? That's 10. How do you represent 10 in denary? That's going to be 1010, which is basically 8 plus 2. Alright, then you have B. What is B? That is going to be 11. That's in binary, that's 1011. Then you have C. What is that? That's 12. So 1100. Then you have 1. That's just 0011. Then you have 2, 0010. Now, in my opinion, at this point, if you guys have an exam on Monday, you should have these values memorized. You should know how to convert small things like 8 bits. Like 4 bits. 4-bit conversions, you should be able to calculate this in your head just by looking at it, okay? So practice till you get that, okay? So and then you just merge these to get 1010, 1011, 1100, 0001, 0010. This is going to be your final answer. That is how to convert between hexadecimal and binary. One more thing, if you're ever given an a group of bits that's not a 4's multiple. Like for instance, you're given 001110. Now, if you start from the right, you'll notice that this divides into this kind of a group. So it's a 00 and then a 1110. If don't get confused, all you need to do is add the numbers to the left so that it's like a group of 4. So I can add 2 zeros. Or if it was something like 01110, I'll split this and I'll realize that I have only 1 bit, so I'll just add 3 more zeros to the left. Alright, don't get confused. And then you just like convert this back, so this is going to be 0 and then E. Alright, that's how you convert between hexadecimal and binary. Alright, so any confusion between converting between denary to binary or hexadecimal to binary? Any confusion, guys? I'm looking at the chat. Okay. Alright, simple. Okay. When asked to convert denary to hexadecimal, would you prefer? Okay, now let's convert to, yeah, okay. So, converting from denary to hexadecimal. Now, this is a really controversial topic. What I like to do and what I did for my CAIE examination, any number that you were given, whether it was a hexadecimal or a binary, all I did was I converted that number to binary and then I converted that number to the other number system. So for instance, if you were given a number like, let's just say you were given a number such as 600, or actually no, let's just say something like 400. If you convert this to binary, okay, if you convert this to binary, this would end up being something like, if we look at it from like a 12-bit register, so 2048, 1024, 512, 256, 128, 6432, 16, 8, 4, 2, 1. You'll also realize now why I asked you guys to have bigger numbers memorized earlier. So this is gonna be 0001, I think a 0, I believe, yeah, 0, and then a 1, and then another 1, okay, and then another 1, wait, no, I think I messed up somewhere. Sorry, no, this would be a 0001. So, and then you got a 0, 0, 1, 0, 0, 0. So yeah, you can see why this method might be a bit too much because of how large numbers get, but it's basically going to end up being like this. Okay, now you can just convert this number to hexadecimal. Again, start from the right. This is going to be a space, this is going to be a space, and since we have an extra number, why do we have an extra number? Okay, this should be here and this should be here. Alright, why did we have it? Let me just confirm one sec. 128 plus 16. Yeah, okay. So now that you have it in groups of 4, okay, what you can do is you can convert this to hexadecimal. So this is gonna end up being 190. So 190. Alright. Now, if you don't want to do so much little maths, then you can do big maths. What does that mean? What you can do is you can have this number and then you're going to divide it by 16, okay? And in terms, what you're going to get is you're going to get the remainder and then the quotient, which is going to be, so for instance, 400 divided by 16. This is going to give you, good point, what is this going to give me? I think this is gonna give me, oh my god, you need to use long division for this. Let me just bring out my book. I always hated long division. I really don't suggest long division, but yeah, it's gonna give you 25 remainder 0. Yeah, it gives you 25 remainder 0. Divide this by 16 and you're gonna get you're gonna get 1 remainder 9, and then divide that by, wait, no, I messed up somewhere. No, I didn't. Okay, This is going to give you 1 remainder 9. Then similar to how we worked with the binary thing, we're going to go from bottom to top. So this is going to be 190. I hate this method, but it's smaller as compared. Okay. So the first way that you can do this is to convert denary to binary and then to hexadecimal. Alright. The second way is to use LCM. Alright, you can go with either of these two methods. Even better if you do both of them. Depends on you. Alright, that's the first way to convert from denary to hexadecimal. Now, in order to convert from hexadecimal to denary, what you do is you take your number, like let's just say I have 190. Let's just take 190. Okay, convert this to binary. You're gonna end up getting 001 1001 000. Now what you want to do is identify the register. So this is just gonna be 2048 1024 512 256 128 64 32 16 8421, and then you convert this to binary. So this is just gonna be 256 plus 128 plus 16, which is gonna be 400. This is the first method. Okay, this is the first method. For this, obviously you need to know the 2's powers, which again, really easy to know. Just start from 1 and then keep on multiplying that by 2. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and then so on. Okay, this is the first method. The second method is a bit more complicated. Imagine you have a hexadecimal such as A10. Now, what will you do here? All right, the second method basically says that you take A and you multiply it by 16 to the power of 2, which is just 256, plus 1 multiplied by 16 to the power of 1, which is going to be 16, plus 0 multiplied by 16 to the power of 0, which is just going to be 1. What just happened? Let me explain. We know that in registers we have, in binary register you have 2 to the power of the position. In denary you have 10 to the power of position. In hexadecimal you have 16 to the power of position. So if you look at this position right over here, it should hold the value of 16 to the power of 0. The next one should hold the power of 16 to the power of 1, which is basically 16. The third one should hold power to 16 to the power of 2, which is 256. That's basically what happened. Alright, so what you're gonna do now is you're gonna do basic multiplication. So A is 10, as we remember, A is 10. Alright, so we're gonna do 10 times 256 plus 1 times 16, which is just gonna be 2560 plus 16, which is gonna be 2560 plus 16, 2576. This is the first way to convert a number like this. The second way is obviously convert the hexadecimal to binary and then to denary. So like for instance, A10 in binary would be 1010 0001 0000, and you're gonna use these same registers, so it's gonna end up being 2048 plus 512 plus 16, which is basically equal to plus 512 plus 16. This is gonna be 2576. Pretty easy. All right, the first method, again in hexadecimal to denary, the first method is to convert the hexadecimal to denary, and then you're gonna convert that convert the hexadecimal to binary, and then you're gonna convert that binary to denary. The second method is to use the hexadecimal powers. Okay, so this converting to binary and then converting to the other base, that's just a workaround, you can say. All right, any confusion so far between these conversions? Any confusion at all? Any questions, anything like that? They'll be fine with converting hexa to binary. Honestly, listen. When you're choosing the hexadecimal to denary, me personally, I always went with the binary, converting to binary method. I mean, it doesn't kill anybody. Okay, it doesn't kill anybody. It's not that big of a deal. But to be honest, go with both methods. Just like do both for confirmation. You know, you get that sense of self-relief as well when you get the same answer using both of them. But obviously don't waste too much time. Do the easier one, and when you're done with the paper, just come back, okay? Alright, so let's move on. What's next? Alright, some theory part to this chapter. You want to know the uses of the hexadecimal number system. 4 basic uses. Let's just go over them in the next 3 minutes, okay? So uses of hexadecimal. So the 4 uses that you should know is error codes, MAC addresses, IP addresses, and HTML color codes. We're gonna go over this a bit more in depth when we're when in chapter 5, right? We're gonna go a bit more in depth, or chapter 4. Chapter 3, I forgot which one, but let's just get a general overview. Error codes, pretty basic. If you ever seen the Windows blue screen of death, you'll know that this is going to be something like 0xFF0011, something like this. Obviously you can see that is hexadecimal. Like you see FF zeros, ones, this is hexadecimal number system. Alright, this is the first usage, okay, to error codes of any operating system or web servers, anything like that. Error codes is the first, error codes is basically the first thing, because obviously you can't go writing the entire error. Like for instance, if my Windows PC crashes due to some memory error, I won't go writing, oh, the memory error is at the position blah 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 blah. All you can do is you can just write the error code 0x blah 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 and say that this is the error, okay? Pretty simple, easy peasy. The second use is MAC addresses. MAC addresses are used to identify a computer. It's basically going to be the address that's assigned to each specific computer. My MacBook has a MAC address, your phone has a MAC address, all of these devices, okay? It's assigned to the network interface card. We're gonna go over this a bit more in the later chapters, okay? But what a MAC address looks like is it looks something like this. AA, I should not use AA, I'm gonna go with MM, II, KK, I'll just go with KK. Alright, so it's gonna be 6 sets of 2 different hex characters. Alright, now one thing that you should know is that the M's usually represent the brand identity, manufacturer identity, and the K's usually represent the serial number. So an example MAC address could look something like 001422, 01203F, something like that, okay? So that's the second uses. IP addresses. Now remember, hexadecimal is only used in IPv4. IPv6. Alright, IPv6. Alright, so how does an IPv6 look like? It looks something like this: FFFF, 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 FFFF. Obviously it doesn't need to be F's, okay? It doesn't need to be F's. It can be anything. Alright, it can be A's, B, C, D, E, 1, 2, 3, 4, 5, 6, 7, 8, 9, zeros, and so on. Okay, so it looks something like this. Okay, one thing that I forgot to mention, MAC addresses, they use dashes. Okay, remember that they mostly use dashes. Okay, they use dashes. Thank you for the reminder. Somebody just messaged that in chat and I forgot. They use dashes. Okay, IPv6 addresses use colons. Okay, just remember this. It's a small key detail, doesn't matter too much, but just remember. Okay, so another example IPv6 address could look something like A8EE, 890F, why am I saying comma, colon 6666 colon 72AB colon 33BF colon 78AE colon 1111 colon 0000. So it doesn't necessarily have to be exactly like this. It can be anything. Okay, it can be anything. So it doesn't necessarily have to be like this. Okay, all it needs to be is it should be 8 groups of 4 different hexa characters. Okay, simple. Now HTML color codes. Each color that you see, it can be represented in the value of RGB or red, green, blue. Red, green, blue. And hexadecimal is used to specify the amount of red, green, blue in each color. So something like hashtag FFFFFF would be something like full red, full green, full blue, which is also just white. Alright, these color codes are usually hashtag XXXXXX, where X is equal to a hexa character. So something like hashtag 12FF32. This is also a valid HTML color code. It's only going to be 6 different hex bits. That is the usage of hexadecimal number system. Now let's move on to binary addition. Alright, so binary addition. Let's say you have two binary numbers. You have the binary number 0101 and then you have the binary number 0001. And you need to add these two numbers. Alright, so in order to add these two numbers, what you're going to do is you're going to use a simple technique. Alright, what I want you guys to remember is 4 key points. If you add 0 and 0, that's going to be 0. If you add 0 and 1, that's going to be 1. If you add 1 and 0, that's going to be 1. And if you add 1 plus 1, that's going to be 0 carry 1. Now, what does this mean? If you convert these to the number systems, you'll see that 0 converted is just 0. So 0 plus 0 is equal to 0. 0 plus 1, that's just equal to 1. 0 plus 1 plus 0, that's equal to 1. Now, 1 plus 1 in normal mathematics, that's equal to 2. And if you notice carefully, carry 1 just means 1 0. And what is that in Denary? That's 2, right? That's just 2. Alright, so that's basically the same thing. So remember, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0, carry 1. Simple. Okay? Alright, so if you have this number right over here, let's go over this one by one, okay? So you want to start from the right side. What's 1 plus 1? Sorry, what's 1 plus 1? That is going to be 0, and then you add a carry, right? So you go 0. Oh my god, what is this stupid ass software? Okay, so that would be a carry of 1. Oh my god, I should probably get an iPad soon, man. Oh my god. Okay, so right now that's just gonna be, oh my god. Okay, okay, so that's gonna be the carry of 1. Okay, I'll just use zeros to signify star. I'll just use stars. Okay, I'll just use asterisks. Okay. Oh my god, you're kidding me. I can't even use asterisks. What the fuck? Okay, dots. Okay, dots. Okay, so all right, so now that's gonna be 0 carry 1, so that's just gonna be 0 carry 1. Now 1 plus 0, or any 3-bit addition, okay, any 3-bit addition, 1 plus 0, you want to start from the top and then you want to go to the bottom. What's 1 plus 0? That's 1. Alright, then 1 plus 0 again, that's gonna be 1 again, so you're gonna type 1 over here. Then you have 1 and 0, you're gonna type a 1 again, and then you have 0 and 0, then you're gonna type a 0. Got pretty confusing? I'll explain again. Imagine you have something like the addition of 1 and 1. This is going to be 0, and then you're going to carry off 1 to the left side, right? So it's going to look something like this. Alright, that's what it's going to look like. Oh my god. That's what it's going to look like. Okay? So in turn, what you're actually doing when you have a bit more bits is just going to do this starting from the right side. Okay? You're going to start from the right side and you're going to do this. Okay? Then what you have is do it on a whiteboard. Is there a whiteboard here? I'm pretty sure there should be. Come on, Obsidian, make me proud. Show me a whiteboard, man. Come on, show me a pen, bro. I just need a pen. Hold on. Bruh. Okay, I don't think that it has a whiteboard. What is this? Oh, yo. Okay. Yo, let's go. All right. So, okay. So, I doubt my drawing is that good either. Okay. So, right. Okay. So, if you have a number such as, oh my god, that's big. Let's just say you have a number such as 110 1, and then you're adding this to I'll get out my mouse, just give me a sec. Okay, so you're adding this to let's just say 0 1 0 0. So you're gonna start from the right side. Okay, you're gonna start from the right side, and you're gonna do 1 plus 0. That's just gonna be 1. Okay, then you're gonna do 0 plus 1. That's gonna be 1 as well. Okay, then you're gonna do 1 plus 0. That's gonna be 1, and then you're gonna do 1 plus 0. That's gonna be 1. Now, one more thing that you guys are gonna notice in binary addition is you are going to see that you can convert these binary numbers to their Denary form. So 8 plus 4 plus 1. What is that? That's just equal to 14. Right? No. That's equal to 8 plus 4, 12, 13. Sorry. Yeah, that's equal to 13. And then you're going to notice that this is equal to 2. What's 2 plus 13? That's 15. Right? And this is just equal to 15. Right? So this is something that you have to understand. Okay, if you add binary, it's going to be the same as adding the two denaries. Okay, though don't ever do it this way. Don't do it this way. This method is discouraged. You are supposed to show working. Now another thing is 3 binary additions. Okay, 3 binary additions. So for instance, you have a number such as 0 0 0 1 1 0 0 0 0 1 0 1. Sure, let's go with this one. All right, now in this case what you're supposed to do is you're supposed to first add the first 2. Okay, so first 2 binary bits. Okay, so what's 1 plus 0? That's going to be equal to 1. Okay, so you have 1. Now you want to add this one and then this one, so that's going to be 0, and then you're going to carry on 1. All right, so basically if you have multiple bits, then you can just start from the top and add it to the bottom one, and then add it to that to the bottom one, and then so on and so forth. So 1 plus 0, what's that? That's 1. Then you 1 plus 0 again, that's still 1. 1 plus 0, 1. Then again here 0 plus 0, 0. 0 plus 1, 1. Then again 0 plus 1, 1. 1 plus 0, 1. Alright, so that's the 3 bits addition. Okay, so that's how you add binary numbers. Okay, and if you, again, normally it's going to be much larger. We're going to cover this in the past papers thing. But if you have something like 0 0 1 1 1 1, and then you add 1, let's just do a large number real quick. You add these, and then you in terms get 1 plus 0 0. 1 plus 1 0, carry 1. 1 plus 1 0, carry 1. Okay, so 0 plus 0 0. 1 plus 1 0, carry 1. All right, and then 0 plus 1, that's just going to be 1. 1 plus 0 1, 1 plus 0 0, 1, and then 0 plus 1 1, 0 plus 0 0, and then 0. All right, that's how you add binary things, whatever. Okay, so that's how you add binary numbers. All right, simple thing. One thing that you're going to notice is something called an overflow error. An overflow error is basically when the value of binary in the final register exceeds what it can hold. All right, that's the basic definition, the one that you should write in the CAI examination. Let me find that. Okay, it's probably somewhere over here. All right, the result of carrying out an addition that produces a value too large for the register to hold. All right, so what this means is that if for instance you have something like 1 1, if for instance you have something like 1 1 1 1, and then you add 0 0 0 1 to it, you're gonna notice that 1 plus 1, that's 0, carry 1. All right, 1 plus 1 again, that's 0, carry 1, and then you do 0 plus 0, that's gonna be 0. 1 plus 1 0, carry 1, so 0 plus 0 0. 1 plus 1 0, carry 1, and that's gonna be 0, and then you add 1, That's going to be 1. So you're going to notice that you have an extra bit. Okay, this extra bit is what we call it as the overflow error. Okay, that's how you add binary numbers. Any questions? Very simple thing. We also have to signify an overflow when adding binary numbers in a large space. But what do you mean by a large space? Alright, so just explain what you mean by large space. One more thing, guys. In all of these conversions, don't ever, again, the examiner does not like that. Don't convert this to Denary and then add that and then just convert that to binary. Don't do that. Do that only for double checking. Okay, so like after you've done a conversion like this, you want to convert this to Denary, and then you want to convert this to Denary again, and then you can see that this whole thing represents 16. Don't use this method. Use the use the binary addition method, and then just use this as a method to double check. Okay, so since there are no questions, let's move on to logical shifts. All right, let's move on to logical shifts, and all right, let's move on to logical shifts. So in our syllabus, there's 2 types of logical shifts. Types of logical shifts. There's going to be the left shift and then the right shift. All right, so the left shift is basically going to be something like, let's just imagine you have a number like 00001100, and you want to shift this 2 places to the left. All you gotta do is you want to completely remove the 2 bits that are at the leftmost and then add 2 to the right, 2 zeros to the right. So what does this mean? I'm going to take this number 00001100. I'm going to remove the 2 bits on the left, and then I'm just going to add 2 bits to the right. That's literally it. That is what a conversion to the left means. Okay, now what does this mean? In this, let's just say, what effect does this have on the final value? The left shift is equivalent to multiplying the binary number by 2. Okay, so for each shift it's multiplied by 2. So like for instance, if I convert this to Denary, all right, you can see that this is going to be 8 plus 4, so that's just 12. All right, now since I shifted this 2 places to the left, that's going to be 12 times 2 times 2, all right, which is going to be 12 times 2, 24, 48. And if you convert this, so that's going to be 32 plus 16, that's equal to 48. So effect multiply by 2. All right, that's the effect of shifting to the left. Okay, multiply by 2 or to the power of shifts. So like you can see this is just 2 squared. All right, so you can see that this is just 2 squared. All right, so since I did 2 places to the left, or if you want to predict the result of 00010010, shift 3 places to the left, or result after 3 places. You're just going to convert this to Denary, which is going to be 16 plus 2, which is equal to 18. Multiply this by 2 to the power of 3, which is just equal to 2 times 2 times 2, right? Which is going to be 18 times 2 times 2 times 2, 144. And if I shift this 3 places to the left, we're going to get 1001000. And if you convert this, this just becomes 128 plus 64, 32, 16, which is equal to 128 plus 16. That's equal to 144. All right, pretty basic. Now let's look at right shift. It's the exact same thing. If you have a number such as 00110011, and you want to shift this 2 places to the right, what you want to do is you want to cancel out the rightmost bits, and then you just want to add zeros to the left. So this would end up being, so like 00110011. What would this be? This would be just cancel out the 2 bits on the right, and then we add 2 zeros to the left. Pretty basic. All right, simple thing. Let's take another value such as 00110000, and we say shift this 3 places to the right. All right, am I still lagging? Yo. Am I okay? Is am I still lagging, guys? Uh, is my stream clear now? Is my yeah? Okay. Okay. All right. So, as I was saying, did you guys get this point? Did you guys get the initial point, or was I lagging back then? Okay, perfect. All right. So, shifting this three places to the right. So the number 00110000, shift this three places to the right. You drop the 3 bits on the right, and then you add 3 zeros to the left. Now, in this thing, what happens is that the effect is divide, my bad. Divide by 2 to the power of shifts. Sorry, it's divide to the 2 to the power of shifts. All right. Can't see screen. Can you guys see my screen? Oh, okay. All right. So let's just convert this to Denary real quick and see what effect it has. So this would be 32 plus 16, which is basically 48. Now this converted is 4 plus 2, which is equal to 6. So 48, and we want to see the effect. So we basically divide this by 2, multiplied by 2, multiplied by 2. Okay, all you can say that this is 48 divided by 2 to the power of 3. All right. So what does that? Oh my God, what the hell? Okay, what does that look like? This is going to be 48 divided by 2, which is 24 divided by 2, 12 divided by 2, 6. All right. You can put this in your calculator. Oh my God. Okay. Is it still lagging? It's still lagging. Am I still lagging? Am I still lagging, guys? Oh my God. Okay. Is my voice better now? I changed my Wi-Fi. Okay. Are you guys able to see my screen? Okay. So we divide this by 2 to the power of blah blah blah. Okay, so you get 6. Okay, that's right shift. Any questions regarding the shifts? Okay, great. What's next? 2's complement. Okay, let's do 2's complement. Now, wait. When we for example move 2 places to the left, will be 4 added? Will we add 4 to the result? What do you mean, like 2 places to the left? No, the effect is basically multiplying by 2 to the power of shifts, or dividing by 2 to the power of shifts. Okay. Yeah, so you will multiply by 4. Okay, you will multiply by 4. Can you explain what the leftmost bit is? Okay, let's get into the 2's complement. Now, in binary, you can represent negative numbers. All right. So, for instance, negative 64 can be represented in binary. We call this 2's complement. Basically, in 2's complement, if you have a register like 64, 32, 16, 8, 4, 2, 1, you're basically saying that in this register, the leftmost value is negative. Okay. Remember, if they ask you to do 2's complement, they're going to mention 2's complement in the question. Okay. Don't assume that the leftmost bit is always negative. They're going to mention that in the question. Okay. So, minus 128, 64, 32, 16, 8, 4, 2, 1. Now, the conversion is basically the same if you want to convert a 2's complement number to Denary. All right. So, for instance, you have something like 10010001. If you want to convert this, and this is a 2's complement number, you just do the subtraction method. Okay, you just do the subtraction method, which is going to be minus 128 plus 16 plus 1, which is equal to minus 128 plus 16 plus 1 minus 11111. That's basically to convert from a binary 2's complement to a Denary 2's complement. Okay, so that is going to be that. All right. So then, if you want to convert a Denary number to a binary 2's complement, all right, what you want to do here? Okay, what you want to do in this case? Let's look at that. a bit. All right. So how does this work? You want to first convert this binary number to Denary number to binary. all right, without the negative sign. So 74 converted to binary, I'll just do it for you guys, would be something like 0, 1, 0. I think, no, we're not going to do that. 0, 1, 0, 1, 0. Yeah, this would be 74 in binary, okay? So you have this as the positive 74, okay? Now what you want to do is you want to invert the bits, okay? Invert the bits. We call this the 2's complement method. You want to invert. I'll draw instead. Sure, I'll draw instead. So if you have a number like okay, if you have a number like minus 74 in binary, this will look something like 0, 0, 1, 0, 0, 1, 0, 1, 0. Hopefully me drawing is easier for you guys. Okay, so this would look something like this, right? So you want to remember that this is the Denary value for 74. Now 2's complement, it contains of 2 steps. The first step, 3 steps, sorry. The first step is to convert the positive number to binary, which we just did. The second step is to invert the ones and zeros. So the 0 becomes a 1, the 1 becomes a 0, the 0 becomes a 1, 1, 0, 1, 0, 1. Alright? The third step is to add 1 to this final value. Alright? So this is going to be 0, you add 1, and then that becomes 1, and then the remaining will be the same. Alright, so it's a mix of binary addition and inverting. Alright, and this is going to be your final 2's complement value. And you can double check 128 plus 32 plus 16 plus 4 plus 2 minus 74. That is 2's complement. So let's just write down the steps and move on to the next topic. Step 1, convert positive number to binary. Step 2, invert ones and zeros. Step 3, add 1. That's 2's complement. Any questions? I don't think anybody wants me to go over how this whole thing works because that's not part of our syllabus, but if you guys want, if you guys are curious, I could spend like 5 minutes trying to explain why this works. Okay, no worries. Okay, let's ignore that whole thing. It's really fun. It's a really fun history. Okay, so that's 2's complement for you guys. All right, moving on. What else do you have? Hey, let's finally go. Okay, now let's move on to the theories parts of chapter 1. Okay, let's move on to the theory part of chapter 1, which is going to be text, sound, and images. Now this is basically memorization besides the file calculations. Alright, so let's start off with ASCII and Unicode. Alright, so ASCII is basically American Standard Code for Information Interchange. Alright, now what ASCII and Unicode are, these are basically, both of these, Unicode and ASCII, are character sets. Alright, what is a character set? Character sets is basically a set of different values that are used to represent characters. Alright, pretty simple. Now, what does this mean? Alright, what does this mean? Imagine that everybody in their childhood, you guys have created your own secret languages, right? You go something like, AY is basically A, or writing with your cousins or siblings or whatever, you guys make up like a secret language. You say that, if I type the number 809, that's basically equal to A, 810 is basically equal to B, so something like 809, 811, 810, 810, you would write this as ABB, something like this. Alright, so what ASCII and Unicode are is they basically take characters like the ones on your keyboard, A, B, C, D, E, F, G, and they assign different denary and binary or hexadecimal values to it. That's basically what ASCII and Unicode are. There are tables to reference these different things. Okay, so for instance, let me explain to you guys. Something like the small a, that is basically in denary or decimal, whatever, that's basically equal to 97. Alright, and then B is equal to 96 and 98, and then C is equal to 97, 99, and so on. All right. So basically, ASCII and Unicode, these are just a big table to reference different characters and their denary/binary values. Okay, that's literally ASCII for you. All right. So, and Unicode is the same thing. Okay, Unicode is the same thing. These are basically character sets. Okay, these are basically character sets. All right. So, let me just explain to you guys how something works. Okay, on your keyboard, every time that you type an A or a B or a C or a D, whatever, every time that you click on these keys, do you think these directly go and store like that in the computer? They don't. Remember, computer only recognizes binary. So what happens behind the scenes is that every time I type a small a in the chat, what happens is that small a gets converted into binary. And how does it get converted into binary? Using a character set. Alright, so like I said, 97, that's basically what gets stored in the computer. Alright, what is 97 in binary? That's going to be 0, 1, 1, I think another 1, no, 0, 0, 0, 0, 0, 1. That's what gets stored into the computer. Alright, that's what ASCII and Unicode are used for. They are character sets that are used to reference binary values to their respective decimal values. Okay, that's basically what these are. Now there's another thing, it's called extended ASCII, which basically supports more characters. All right. Now, something that you should know is that in ASCII, what you have is that you have limits like 0 to 127 in Denary. I'll explain what this means. And 00 to 7F in hex. Alright, in extended ASCII you have 0 to 255, yeah, 255 in Denary, and 00 to FF in hex. You don't need to memorize these essentially, okay? You don't need to memorize these essentially, but this is basically like just for your general knowledge. What this means is that, for instance, if you have in ASCII, if I pull up the ASCII table, let me pull up the ASCII table for you guys real quick. ASCII table. Okay, so I don't think I can find it. Okay, I found it. So let's just copy paste. All right, come on, please show me. Okay, so you guys can see in this ASCII table, you guys can see that these values in decimal. I'm sorry for the color thing; it's really weird. Come on, please show me. I can't make it white. Let me make it white, bro. Okay, never mind. So you can see that in the decimal area, this goes from 0 to 127. Alright, so you can see all these characters being represented. Okay, you can see all of these characters being represented. And in the hex, it goes from 0 to 7F. So that's basically what I mean when I say that these are the limits. In extended ASCII, there's obviously more characters, which means more limits. Alright, any question regarding character sets? Anything at all? Let's just write down a few disadvantages of ASCII. Is that ASCII doesn't represent international characters such as Chinese letters, like Chinese letters or Greek letters, which is why Unicode is preferred, because Unicode has all of that. Okay, and yeah, okay. Okay, so that's basically where Unicode comes in handy. Okay, that's how Unicode comes in handy. All right, so what else? Okay, any questions regarding either of these? Okay, what do you do when it asks answer for 4 marks on the same? I'm good. Wait, which questions? Okay, that's something else. I have the list of ASCII and extended ASCII, but I can't. No need. You don't need to memorize each character. Okay. I don't think they've ever asked about the different characters and their values. Is Unicode 16 or 32? I'm gonna guess that you mean 16 bits or 32 bits. It's actually I believe both of them, because it uses 16 bits and 32 bits to represent different characters. So yeah. How is text converted to binary? That's an incredibly good question. Okay, let's I explained that earlier again. I'll go over it again. Let's say I type something like A into my keyboard. Okay, let's say I type something like A in my keyboard. Now let's just say that I'm using ASCII. In ASCII, A is equal to 97 in Denary. Okay, so you basically convert this 97 to binary, which is basically 01100001. That's how you convert from like a letter to binary. All right, you use these character sets. In Unicode, it gets a different value, but basically this is how you do it. Each character is referenced by a thing. Okay, so like for instance, I can go around saying that, oh, that guy, his name's Adam. Just like how we talk about our names. All right, there's a lot of people, we reference them by their name. Similarly, each character has a value to it. All right, each character is a person, and their name is basically their binary value. Okay, so besides this, let's move on to representation of sound. All right, let's move on to sound. All right, so one sec, I'll be back. क्या कर रही हो, क्या चाहिए?
मोबाइल दो मेरा.
दरवाजा बंद कर दो. Alright, let's move on to sound. Okay, so sound. Let's take a quick physics lecture as well simultaneously. Each sound wave looks something like this. Okay, no, well, not like that, but like it looks something like this. Okay, this is how a sound wave looks like. Obviously better drawn. My drawing skills suck, please do not mind. And basically what we say is that this duration over here, this is called a period, and basically if I draw a line here, we say that this is like the wave's frequency over time. Okay, this is like basic sound knowledge. Okay, you do not need to know this, I'm just saying this for example. Now in sound, the number of bits in a sample. Okay, what is a sample? Let's just talk about what a sample is first. Okay, so obviously we can't store waves inside of a computer. So what we do is we basically use its frequency, wavelength, and amplitude to sample it. Okay, sampling means we basically measure the amplitude, which is basically this distance of the sound wave. So sampling means measuring the amplitude of the sound wave. And this is done using an ADC, or an analog digital converter. Alright, and now a few definitions that you should know about sound is the sampling rate resolution. Alright, one thing, if you ever see the keyword resolution, you should know that this basically refers to the number of bits in something most of the time. Alright, so for instance, sampling resolution, this would be number of bits in a sample, or something like your screen resolution. What does 1920 by 1080 mean? It means 1920 by 1080 pixels, right? Resolution is usually referred to something, some amount, some number of something in something. Okay, so sampling resolution is number of bits in a sample. All right, so then you have sampling rate, which is number of samples taken per second. Now let's go over this. So obviously in a sound wave, you're not just going to take one amplitude and say that this is the entire of the sound wave. You're obviously going to go in sequence. You're going to go in like blah, 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 blah. And obviously the more samples you take, the better the sound quality is going to be. And the amount of samples you're taking per unit time or per second is basically called the sample rate. Okay, that's how the sample rate and sampling resolution works. Okay, any questions? Okay, no questions. Alright, let's we're gonna get to the kibibyte thingy in a while. Alright, let's talk about bitmap images. Images can be used to store as in binary values. Okay, so for instance, if you have an image, something like let me just do some professional drawing. So you have this guy over here. Let's give him a smiley face. Let's give him a crown as well. What else? Let's make him hold a laptop or a small house. Yeah, let's make him hold a small house. It's at a window. Alright, so you have any different what do you say, if you have a picture, each pixel in this picture, it's referenced by binary. So like for instance, the blacks are referred by 000000. The whites in this picture are represented by FFFFFF, which is HTML color codes, which we talked about before. So bitmap images basically contain pixels. Okay, bitmap images are made up of pixels. All right, two-dimensional. Obviously this is going to be two-dimensional. Okay, so don't worry about that. Okay, so a black and white, so there's like different colors. Okay, so for instance, if you have a black and white image, that is referenced as just 1 bit, because you can just use like 1 to signify white and 0 to signify black. Or if you want a more dynamic range, you obviously add more bits. Okay, you add more bits, which is where the term color depth comes. Okay, color depth is the number of bits used to represent a color. All right, so for instance, the more bits you have, that's going to be the more bits you have, that's the amount of bits that's used to represent a color. So the more bits you use, the better the color is going to look, right? Basic maths, basic general knowledge. Now, image resolution, like I said before, anytime you see a resolution, it's probably a number of something that is used to represent something. In images case, it's the number of pixels used to make up an image. All right, obviously the more the resolution, the better the image looks, but again, size matters, which brings us to our next and final topic. Yeah, okay. Now, any questions so far? Any questions so far? Any questions so far? If there's no question, I'll be back in 2 minutes. I'll be back in 2 minutes, and we'll continue. Okay, I'll be back in 2 minutes. I just gotta get some water. I'll be back in 2 minutes. Get water. Alright, I'm back. Alright. So any questions so far, guys? Else let's move on to the final part of chapter 1. Any question? Do we need to know vector images? Let me check actually. Let me open up the syllabus and check. I've never learned about vector images, but holy shit, who that down? Do that on Netflix. Okay, there we go. Vector images. I learned about that in AS, not in. Wait, hold on. I'll check the syllabus. Sound wave sampling resolution. Blah 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 blah. one more thing that you guys should know is that Unicode requires more bits per character, but that's like general knowledge. Okay, ASCII uses less bits, Unicode uses more bits, but bitmap, I don't think that you need to know. I don't think you need to know vector images, but you should just know that what vector images are. It's not that complicated. Vector images are just like computer images that are created using like mathematical commands, right? So it's just images using maths. You don't need to know that much about it, okay? It's basic stuff. Anyways, moving on to the final part of chapter 1, which is data. Yeah, data. Let's just call this data. Okay, fun stuff. I used to love this chapter. So, Unicode versus ASCII. I'll just go over it real quick. In Unicode, you have more bits to represent different characters. Okay, Unicode has more languages, more supported characters. So like Greek, Chinese, and so on. Okay, and Unicode is much more extensive. All right, it's a newer version. It's a newer character set, and that's basically Unicode for you. All right, so data, pretty simple. Let's go over the measurement first, which is going to be now. This is all. This is quite. What do you say? This is. It's a bit. People think that it's a complicated topic. It really isn't. Okay. So let's just go over there. There's two types of measurements of data. The first one is using tens powers, and the second one is using twos powers. What do I mean by this? If you have something like 1 kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, which I guess is like the biggest that you can get in our syllabus. What this means is that you basically have 1,000 bits, 1,000 bytes, 1,000 bytes, 1 million bytes, 1 billion bytes, and so on, right? So if you remember physics, you'll remember this. What do you say? You'll remember you're learning these units in physics as well. So kilo, like kilogram. What is kilogram? 1,000 grams. What's megagram? That's 1,000,000 grams. What's gigagram? That's 1,000,000,000 grams. What's teragram? That's what do you say? A trillion, right? And so on. So it's basically tens powers. Okay, that's basically tens powers. Okay, so then you have so basically you refer to these as tens powers. All right, so kilobyte is basically 1,000, and then 1,000,000, and so on. That's basically what that is. Second thing is the twos powers one, which is known as kibibyte, mebibyte, gibibyte, tebibyte, pebibyte, exabyte, and so on, which is basically 2 to the power, right? Simple stuff again. So kibibyte, basically what this is that it's basically 2 to the power of 10, 2 to the power of 20, and so on. What this means is essentially what you have in kibibyte is 1024. What you have in mebibyte is 1024 times 1024, which is basically 1048576. You don't need to remember this, okay? You don't need to remember this. I'll show you like a simple technique for these calculations when we do the past paper things. But you should know that kibibytes are used to refer to 2 to the powers, and the kilobytes are used to refer to 10 to the powers. One more thing, these are usually referenced by KB, MB, GB, and so on, whereas these are referred to as KIB with a small I, KIB, MIB, GIB, and so on. Okay, that's how they're referred to as. Okay, we're gonna get over the calculations. Okay, so what else do you have? What else do you have? You have the calculation of file size. Okay, so calculating file size, pretty simple. So for images, I'll just write this down over here. Actually, it makes much more sense to write this down over here. For images, file size is going to be resolution multiplied by color depth. It's pretty simple maths. If you have a 10x10, okay, let's just say you have a 10x10 image, okay, you have a 10 by 10 pixel image, so it's a 10x10 image. all right, and you're using, how many pixels in total is that? That's going to be 10 times 10, right? That's going to be 100 pixels, all right. Now let's just say that each pixel is worth 8 bits, all right. So in order to calculate the final size, all you need to do is multiply the 100 by 8, all right. So I'll also write this down over here. For instance, a 100x100 image with color depth 8 bits. What is this gonna be? This is gonna be, the resolution will be 100 times 100, which is equal to 100,000 pixels, and color depth, and the final size is just gonna be this multiplied by 8 bits, which means that it's gonna be 800,000 bits, and then you can go on and converting this. Okay, simple. All right. In the case of sound, you have what do you say? This file size in sound will be image resolution. Sorry, what am I saying? Would be sample rate multiplied by sample resolution, or I'll just write resolution multiplied by length. All right. Let's look at this from a more wider perspective. Where is it? Okay, so a sound wave, let's just draw another sound wave, which goes like this. Now, what you're essentially doing is that this is basically over time, right? Now, you're calculating the sampling rate, which is the number of samples taken per second, multiplying this by time, and then you're multiplying that by the amount of bits that's used to represent each sample. Okay, so pretty simple. So that's how you calculate sound's file size. All right, any question before we move on to data compression? So do I multiply every number written in the question? I mean, it's controversial. Sometimes they're gonna mess it up for you. All right, remember, these are all in SI base units. So like sample rate, you're gonna take this in hertz. Resolution, you're gonna take in pixels. So don't fall for their kilohertz if they ever, I don't think they pull that off, but like, remember, it's gonna be the base units, right? We're gonna get to data transmission in like 10-15 minutes. This topic is almost over. All right, so next up you have data compression, I think the final part of this topic. No, yeah, the final part of this topic, data compression. All right, so in compression, basically, why do you do compression? You save storage space. So like, for instance, if you have like all those Barbies on your computer, you guys, I know about the Barbies on your computer, you want to compress them so that it doesn't take up that much storage. Okay, you want to compress all the Barbie movies so that it doesn't take up that much storage. You basically use compression. Okay, so compression is used to save storage space. Okay, reduce time taken to stream videos, reduce time taken to download/upload files. All right, basic stuff. Okay, you take this and you basically just use this to store data. Okay, you reduce their file sizes. Now there's two types of compressions in our syllabus. There's the lossy compression, there's the lossless compression. All right, let's go over each of these. In lossy compression, once you compress the data, it cannot be recovered. Like the original copy, original form cannot be recovered. All right. So, an example of this would be in images, for instance, images. You can say that it basically reduces color depth, right? By removing colors the eye cannot see. Like obviously, if as a human you can't see a certain color, it's gonna remove that color from the image, right? Or in the case of sounds, it reduces sounds inaudible to the human, inaudible to humans, right? So if a sound has a high frequency, it basically revokes that. All right, that's how lossy compression works. Basics of it. Examples are MPEG-3 files, I believe. Yeah, MPEG-3/MPEG-4, which is basically MP3, MP4, you know. Right. Yeah, and then you have JPEG files for images, right? So this is for audio, video, images. Okay. So I believe. Hold on, just give me a sec. All right. Also, I saw somebody say that the other day. I saw someone say that nibble is not in your syllabus. That is false. A nibble is indeed in our syllabus. So don't listen to anybody who says that it isn't. A nibble is in our syllabus. Okay. It is in our syllabus. Don't worry about that. Okay. So yeah. What was I saying? What was I saying? Right, right. Okay, so obviously, reduced time to take in, or you can also rewrite this as reduced bandwidth required. All right, reduced bandwidth. All right, and so on. All right. So, what else? And you can rewrite this as like shorter transmission time, so on and so forth. Right. What was I gonna say? Right, and then you have lossless compression. Okay, and then you have lossless compression. You can also like write this in simpler form. Reduce the sound by reducing the sample rate, sample resolution by removing sounds inaudible. All right. So if you want to go for the technical definition, this is how it works. And if you want to go for the simple definition, that's this. Okay. So that's lossy compression. In lossless compression, once you compress the data, the original data can be recovered. Alright, so in the case of lossless, what you have is you have the most common thing, which is run length encoding. Alright, let me just okay, run length encoding, RLE. So imagine that you have a sequence of letters. Let's just say you have a sequence of A, B's, C, D's. Alright, so you have this all stored in the file. What you can rewrite this as is you can say 6A, 7B, 7C, and 4D, which is obviously much smaller than writing all of this. So instead of my friend coming up to me and going like, hey Ateeb, A, B, 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 C, 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 D, 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 D. He can just go like 6A, 7B, 7C, 4D. Make life easier for the both of us. Okay? Make life easier for the both of us. That's run length encoding. The technical definition is it's a form of compressing data in a way where it can be recovered. And yeah, that's basically the technical definition. Remember, RLE is only effective when there's a sequence of values, or when there's a sequence of repeated values. So if you look at something like A, B, C, D, if you use this on RLE, you would go something like 1A, 1B, 1C, 1D, which basically refers the entire method useless, right? So remember, it's only effective when there's a sequence of repeated values. And yeah, this is also used on images. So for instance, if you have an image that is like, let's just say you have an image that is colored. Okay, let's just say that you have an image that is in binary. It looks something like 1000011, or like let's just say that it looks something like www bb www. You can use RLE on this, so it looks like 5w2b, 2b, 1w, 3b, 2w. Obviously, it basically reduces the file size. Okay, so that's how run length encoding works. Any questions? W. All right. Any questions, guys? All right. With that, we can conclude chapter 1, and then let's move on to chapter 2 in like 5 minutes. After 5-minute break, I need to take a breather. One thing that you guys should know, same thing I told last year as well. When I do these chapters, I don't want to just go over them, a one overview. I want to go in depth on them, right? So that's why I take so long to explain a chapter. Plus, last year also I noticed that many people that I did explain chapters to, they ended up realizing that there are other methods to do stuff, and there's things that they don't know. So Yeah, that's why I like to go over everything in depth. Okay, that's why I like to what do you say? That's why I like to make sure that everything you guys know everything so that you're ready for the paper. Okay, so we're gonna start off with chapter 2, which is data transmission for file. You give your calculation in the size that they say. So in the end, they're gonna mention if you want to give it in KIB, in MIB or KB. Always remember they're gonna like try to mess you up. Maybe they say KB and not KIB. So remember the differences between the two. Okay, they're gonna tell you what to say. All right. So let's go do chapter 2, and then we're gonna start on chapter 3. Can we do chapter 3 before chapter 2? The reason I did chapter 1 before any of the other chapters, even though it's like the simplest chapter, was because I tell everybody what happened in chapter 1 so that I can use that to explain chapter 2. Now you're gonna realize when I go over chapter 2, you're gonna realize that I reference a lot of chapter 1 stuff, so that's why I explained chapter 1 first. Similarly, in chapter 3, you're gonna see that I reference a lot of chapter 2 stuff and chapter 1 stuff. So that's why I want to do chapter 3 afterwards. Okay, chapter 5 and 6. We're probably not gonna be able to do chapter 5 and 6 today, because I doubt anybody here wants to stay awake with me till Fajr. So we're gonna do that tomorrow. Okay, 5 and 6. We're probably gonna do that tomorrow. All right. So let's just take a 5-minute breather. I'll be back at exactly. It's currently 21:35. I'll be back at 21:45. Let's take a 10-minute breather. Okay. I'll be back in 21:45. Max Verstappen. Max Verstappen. Max Verstappen. Max Verstappen. I know my mic is on. uh, no, we're going to Max Verstappen. No. I just thought like still have what 4 minutes. Oh, you know what? Oh, you know why I wanted to do this whole thing in a VC? I was really hoping that some business kids would have their session. What do you say? That some business kids would have their session. And last year when I did this, we had like 70-80 people in a VC, right? What I would do is I'd tell them all to spam join the business session. So we'd essentially end up rating their sessions. That was so fun. We'd not let them study, and then we'd laugh at all the business, commerce, economics students, because I hate those guys. I hate business subjects. Forget business subjects. Imagine taking business subjects, bro. Let's do this again. There are no business sessions, man. It's gonna be no fun rating a what do you say an empty VC. That is so mean. Oh man, don't worry about it. I just have personal issues with business subjects. That's I remember one time there was like a single guy in a VC, and I just told like 70 people to just spam join that, and oh man, that was a fun thing. we ain't design we ain't designing homeless shelters for them once they graduate. Oh man, no, I need that shelter. Come on, man. Can't do that to me. I'm gonna be homeless on the street. Come on, you gotta design a shelter. Oh man, those were some fun times, man. I'd ask you guys to like raid one of the VCs they have open right now, but that would mean that I need to leave the speaker, and then I'd have to come back, and then the mods will have to give me speaker again and stuff like that, which is why I would not be fun. Bro, are you from Karachi? Do I sound like I'm from Karachi? I'm not from Karachi, bro. I'm not from Karachi. Oh man, fun stuff. 2 more minutes. No, wait, I just remembered I don't take computer science. Oh, okay. Oh, guys, let me just. I can smell burgerness. I agree. I spent most of my life abroad, which is why, yeah, I suck at Urdu as well. Oh man. Rod, can you do me a favor? Can you like make a poll in the chat and like can you like ask how many of these people want a P2 session as well? just like write P2. Guys, if you like want a P2 session as well, I'll do that as well. That's gonna be like 4 days long probably, because we're gonna dedicate 2 days fully to pseudocode only. So if you guys want to see P2 session, Red, can you make the poll? Also, guys, one more thing. I think the hardest working people, whenever I do these sessions, last year as well and this year, are the mods, bro. Listen, I want to be in the session, okay? I'm supposed to be in the session. You guys, it's your own choice whether you want to leave or join the sessions. But now I force the mods to stay with me for 6-7 hours, bro. Those guys, I do so much wrong to them. It's so yeah, I dedicate like 1 minute to the mods. Those guys are so chill with that whole thing. I can, it's my own choice to join the session and make it last like 7-8 hours. It's your guys' choice. You can leave whenever you want, but the mods, they gotta stay here the entire time, man. Okay, 10 minutes are over. Let's start the second chapter. Oh my god, how long is this? Wait, hold up. I'm gonna see how long this is. Oh my goodness. Okay, how long is that? Ooh, that is long. Okay. Anyways, let's. I should have made this like. I'm just gonna. One sec. I'm just gonna make a note now. That's much more effective. Chapter 2, data transmission, and I'm just gonna zoom in. Yeah. Okay, how do I hide this? How can I hide you? Oh, can I just... Nice. Okay, that should be enough zooming in. Where will you post the recorded session? I'm gonna just like put it on my Google Drive and send the Google Drive link. I tried to record sessions during the summer, but like I made like 5-6 videos on a YouTube channel, and then I just gave up because there was barely one guy with me. So yeah, that was a fun failure. Anyways, how long are you going today, till what chapters? Hope is to go till chapter 4, but we're probably gonna end at chapter 3. We're gonna do chapter 1, 2, 3 for sure today. Alright, let's move on to chapter 2, which is data transmission. Every time that somebody sends a message to you guys, or I send a message in the chat, anything that happens over the internet, it's done using transmission of data. It's data, right? Now, how does that look like from a developer's point of view or a computer science point of view? All right. So imagine that you have something like, imagine that you have point A, which is your house, and you have point B, which is Amazon, and you just ordered 50 freaking Barbie dolls, because that's the kind of people that mostly buy from Amazon. And now these 50 Barbie dolls are in a box. Okay, now this box, obviously this box has your address, your name, your contact information, and so on. All right, now this box is basically taken from Amazon to your house. Similarly, in computer science, you have different servers and you have routers. All right, this router, this is you, believe it or not, you're a computer system now. All right, so you have your web servers. These web servers send you packets and you send them packages. These packages are called data packets. Okay, data packets. Now these data packets basically contain these data packets basically contain what was I saying? Right, sorry. These data packets contain the data header, the payload, and the trailer. Payload, data header, payload, and trailer. So in the end, you can just imagine this entire thing as a big truck. Okay, so somebody said, what if I order 51 Barbie dolls? So then they're gonna use a truck. Okay, so you have your truck, all right, and this truck is attached to a bigger like the cargo. All right, so this truck's front is basically your header, and this is your payload. And let's just say that you attach a small human in the back, so that is going to be your trailer. Okay, so the header is the driver. this knows where it's gonna go. The driver obviously knows where he's going, right? So how do you reference different people? Okay, how do you reference different people? You use IP addresses because everybody has an assigned IP address. Remember, I told this to you guys earlier. So the header contains IP addresses. And which one does it contain? The sender and the receiver. So you can say that IP address of the sender and IP address of the receiver. This is the two, and it also contains some other things about the data packet, such as the data packet size, okay, size of data packet. And it also contains a sequence number. I'll go over this in a while, what this is, okay? I'll go over this in a while. Alright, so these are the phone things that you can say a header contains, or the front of the trailer, which is right over here. Alright, now imagine that I'm sitting over here. If I'm taking the truck somewhere, obviously I know where I'm going and where I'm coming from. So I know the IP address of where I came from and where I'm headed towards. I also know how much Barbie dolls are in my trunk. Alright, so these are the three things I know. Now, what the sequence number is, the sequence number is basically, now obviously you're not going to transmit Barbie dolls on the internet. Alright, you're not going to transfer Barbie dolls on the internet. Instead, you're going to transfer 000111000 blah 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 and a bunch of them. So their sequence is what we call the sequence number. It's just used to check if data was transmitted correctly. We'll go over that in a while. Okay, so let's talk about the payload. This is basically the data being transferred. Oh, sorry, I messed up something. The sequence number is not anything about the payload. My bad. The sequence number is not anything about the payload. Now, obviously, one person isn't going to be the only, one truck won't be used to carry 51 Barbie dolls. There's going to be a lot of them. Alright? A lot of them. And basically, this payload, it's not going to look something like this. On the internet, it's going to be a lot bigger. So there's going to be multiple payloads. Alright? Multiple of them. A lot of them. Okay? A lot of them. And this sequence is basically called the these different data packets, their sequence. All right, so let's just say that I have this is one truck. All right, and I'm just going to copy paste this. I'll explain this better. Okay, I'll explain this better as well. And then you have another data packet, and these are all headed to the same destination. Now let's just say that in this sequence I want this one to arrive first, this one to arrive second, and this one to arrive third. So this truck will have an ID or a sequence number of 1, 2, and 3. So all of the data, when you send a request such as hello, obviously it's not gonna like oh my god, it's not gonna go crazy and send the entire text at once. It's gonna divide this up into different data packets. Okay, okay, and these separately will be sent to the receiver. Okay, so that you have like 1 truck, 2 truck, 3 truck, and they have their different sequences. Okay, so this is the data being transferred. Okay, that's what the sequence number is. Hopefully that's understandable. Looks like a group of people just got squashed by the truck. Anyways, then you have the trailer. Now basically this is used to identify end of the packet, and it contains some form of error checking. We're gonna get this in the end. So like for instance, if you look at a truck from the back, you'll see that it has like some kind of thingy like, oh, this is a truck or whatever. So its ending is basically signified in the trailer. So these things you should know. Okay, everything that I write down, you guys should know what they are. Okay, so anything that I write down, you guys should know what they are. Okay, that's basically what I remember from the marking schemes from the last time I taught this. Okay, so next up you have what else do you have? Okay, so the actual the actual data being transferred. Okay, so then you have this method called packet switching. Okay, so so basically this is when a message is broken down into data packets, what I just talked about. Alright, let's forget about Barbie dolls for now, and let's just look at it like from a good perspective. Okay, so imagine I have a message such as hi, and I have the sender and the receiver. How do data packets actually work? There is a network of routers, which I'm just gonna label as lines, okay? There's a network of routers, and basically the data packets go from different routers and eventually they arrive at their destination, right? So they basically, packet switching is basically that the message is broken down into data packets, and sorry, we refer to these routers as nodes, okay? So each router is called a node, okay? I'll just, oh my god. So there are nodes used to transfer the data packets which contain a router, okay? So what is the router's, why am I saying router? What is the router's role in this, okay? The router determines the path the packet needs to take. Yeah, but that's just it. Okay, let me put this in a more practical manner. Imagine I'm leaving for school and I forgot that I have Google Maps on my phone. I'll go out of my street and I'll turn right, and I wanna know if I should go straight or left. There's gonna be an uncle at the street who's gonna tell me, "Beta, go straight." I'll go straight. Then there's gonna be another intersection, another uncle. He's gonna tell me, "Beta, go left." I'll go left. Then there's gonna be another uncle, and he'd go, "Beta, go right." I'd go right. Eventually, I'll reach my destination. These uncles, they're basically the routers, right? They're basically telling me where to go, and they're gonna tell me the shortest distance. Okay, so router determines the shortest path the packet needs to take. So if we forget about memes for a second, and we have like these different routers, and let's just say that our data packets leave the destination. Let's call this the destination, and this is called the recipient. Okay, it's gonna go to the quickest router, the nearest router, and then it's gonna go, and that router is gonna tell it to go to another router, and then another, and then another, and that's how it's gonna receive me. So every time that somebody like you send a message in the chat, I send hi. Every time that I send a message like hi, it basically gets divided into data packets, gets sent through different routers, and then eventually reaches you guys. That is how it eventually reaches the Discord web servers, who then send it to you guys. But like, that's the same thing. That's how that whole thing works. And yeah, I do agree. Why are there so many Ateeb Suhails, bro? Oh my god. Anyways, that's how packet switching and stuff works. Okay. So besides this, what else? Okay, so now there is a thing that it's called packet hopping. Okay, basically, sometimes the uncles, they're not very good, and they tell you to go a certain way, and you end up getting lost. We call these lost packets. Okay, sometimes during transmission, data packets are lost. Okay, because they keep bouncing. Okay, I'll get to what this means. Okay, what this means is that sometime a data package is gonna go, and then 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 go, and it's gonna go across all these nodes, and it's never gonna reach its destination. These are called lost packets. Okay, now in order to overcome this, we use something that's called hopping. In hopping, we basically, in the header of the data packet, we add a hop number. Every time the packet reaches a router, the hop number is decremented. So let's just say that I have a packet and it goes to the first router, and let's just say it starts off with a hop number of 15. After hitting one router, it'll be 14, and then 13, and then 12, 11, 10, 9, 8, 7, 6, and so on. If the hop if the hop number becomes 0, packet is deleted and asked to be reset. What does this mean? If a packet leaves with a hop number of 15, and let's just say it bounces between 15 times between different routers, it's basically deleted from the system. And then the sender is asked to send that data packet again. That is the method of hopping. Okay, Okay, okay. Any questions? You guys should understand this well enough for the further as we go on. Any questions? Okay, I'm gonna assume no questions. Okay, how do I remember all of this? Conceptualize. That's literally it. This is like the only thing that I've taught so far. And if you understand the concept, you'll get the definitions. Okay, so it's just packet hopping is just like you know that it's gonna start off with an initial number and it's gonna subtract. So all you need to do is actually define this in the Cambridge. Get the concept and you will understand how to explain it. All right. So why am I getting pinged? Where am I getting pinged? IG Computer Science, the goat from last year, Ateeb Suhail, my cutie. What am I reading? What am I reading? What am I reading? What am I reading? Oh my god. Anyways, back to community events. Yeah, okay. Any question, guys? Okay, no questions. Let's move on to data transmission, the official data transmission. Okay, so data can be transferred over short distances or long distances. So I can go from my home to my cousin's home, or I can go from my city to another city. All right, so short distances, long distances, basic distancing stuff. Okay, so in data transmission, you have a few types of data transmission. We refer to these as simplex, duplex. Simplex, duplex, half duplex. Let's go over these, okay? So in simplex, let me just explain it and then I'll get to writing down the definitions, okay? I'll explain it and then I'll get to it. Okay, imagine that I live over here. Okay, imagine that I live over here and my cousin lives over here. And let's just say I want to send him 0, 0, 1. Actually, I want to send him 0, 0, 0, 0 because he's a 0, because he's a loser. So what I'm going to do in simplex, what happens is that I can only send him stuff. Okay, so it can only be in one direction at a time. Okay, so a 0 will be sent and then a 0 will be sent and then a 0 will be sent, only in one direction. Okay, only in one direction. Only I can only send to him. An example of this would be in printers. If you guys print something, the printer doesn't send something to your phone. You're only sending the printer the page that you want to print. That is an excellent example of simplex. Okay, one direction, one at a time. Okay, in the case of duplex, however, he can send me zeros as well. Okay, so sorry, half duplex. He can send me zeros as well. So I can send him zeros and he can send me zeros, but we can't tell each other at the same time. Okay, we can't tell each other at the same time. In the case of full duplex or duplex, I can send him zeros and he can send me zeros as well. Okay, so that's basically how you explain this. Okay, so let me just write this down. In simplex, data is sent in one direction only, and in half duplex, let me just bring half duplex above here. Data is sent in both directions but not at the same time. And in duplex, data is sent in both directions, can be at the same time. Alright, so that's basically what simplex, duplex and half duplex is. Okay, so let's just go over this again. If I have one circle and I'm sending stuff to another circle, in simplex I can only send in one direction. Okay, in half duplex I can send in both directions but not at the same time. In full duplex I can send in both directions and at the same time. Okay, that's simplex, duplex, half duplex. I'll share these notes. Don't worry, it's gonna be in the drive link. Now let's talk about parallel and serial. Alright, let's talk about serial and parallel. Now let's just imagine that I have two big rectangles. Okay, now serial is basically used to serial basically means that there's only one direct line of communication. Okay, so yeah, and parallel basically means that there's multiple lines of communication. Okay, so I'll write these down as well. Serial means that one bit is sent across one channel at a time. We call these wires channels. And parallel, multiple bits, multiple channels at a time. Now, a good way to imagine this. Let's just say that that I have my cousin in front of me and I have myself in front of him, right? And I want to tell him hello, but I want to tell him letter by letter. Obviously, if I want to go with serial, I'm going to tell him H, then E, then L, then L, then O. That's serial. I'm talking to him one by one. In the case of parallel, however, I have multiple Ateeb Sohails who are telling multiple things to him. So like one of the Ateeb Sohail is saying H and the other one is saying E and then the other one is saying L and then the other one is saying L and then O. So there are like multiple wires. There's multiple channels of communication. And they're all telling it at the same time. Alright? So like I said, where did it go? Where did the okay, I think, oh my god, okay, right. So as I was saying, in the case of in the case of parallel, in the case of serial first, there's one line of communication. In the case of parallel, there's multiple. Now obviously, if you have something like, for instance, you have something like you're telling my cousin HELLO. Now there's a chance that he messes up the letter, so he can understand ELLOH. Okay, so like in parallel, because of this, skewing is possible. What is skewing? Imagine that imagine this. Okay, I have me and then I have my cousin, and then there's 5 lines of communication. And let's just use numbers. Okay, so there's 0, 0, 1, 1, 0. Now there is a possibility that when he gets this data, it's not going to be the sequence that I send it in. So let's just say I send it in the sequence of 0, 0, 1, 1, 0. Maybe he receives it at 0, 1, 1, 0, 0. So this is called data skewage, okay? Or in technical terms, if you want to explain it in technical terms, where is it? I'm going to find the marking scheme definition. Yeah, okay. Data that arrives unsynchronized. Data skewing. Data that arrives, skewed data, is data that arrives unsynchronized. Now, one thing that you want to remember is that serial is used for long distances and parallel is used for short distances. Okay? You should know this. Okay? But parallel, of course, is faster. Okay? Parallel is faster, whereas serial is comparatively slower. And what else? Let's make a table actually. Can you make a table in this? Please tell me, Obsidian, you're gonna allow me to make a table. Don't do me like that. Insert table. Yeah, let's go. Okay. So serial, parallel. Okay. So serial, less risk of external interference. Then you have what else? More reliable over longer distance, so used for longer distances. No risk of skewing if amount is small. So less expensive. In parallel's case, you have faster speeds, you have works used for short distances, chance of skewing, more expensive, yeah, okay, that's it. So these are the 2 things. Now you can obviously merge simplex, duplex and half duplex and parallel and simpler. So the fastest method of transmission would be full duplex parallel, which means that you're sending bits along multiple wires at the same time in both directions. Half duplex parallax would mean something like you're sending data in both directions but not at the same time across multiple channels and so on. So you can merge these definitions. Okay. Any questions so far? Any questions so far? Serial is used to signify wires. Okay, serial and parallel are used to signify the amount of channels or the amount of wires. Simplex, duplex, and half duplex are used to signify what happens on those wires. Okay, so simplex is like one bit is sent in one direction only. Serial is that one. Sorry, one sec. One wire sent across one channel exists for data transmission. Am I even recording? Okay, I am recording. Holy cow! It's been 2 hours. Damn. Is there anybody else? Wait, are you recording? Wait, is anybody recording? Oh. Nice. Oh. Okay. What was I gonna do? Right. Any question, guys? What is skewing again? Skewing is basically the data gets messed up in sequence. So if you have a data like 11000, skewing basically means that when it receives, you have something like 001100. 0. Yeah. What is the difference between a node and router? Good question. A node basically is like a station, and router is basically something that exists in that station, I guess. Ateeb, what's your my number 011001101010100110011001100110011. Yeah. Convert that to Denary. Good luck. Yeah, what was I saying? Okay. So yeah, that's any question, guys, before we move on to USBs. What's your town hall level? Town hall level, I think it is 1010. Yeah. Anyways, okay, universal serial bus. Okay. Let's stop shooting. Oh my god. Oh man. Okay, guys, let's move on. Something that I clearly can't do. The fuck? Oh, give me a sec. I need to get something to eat. My brain is going foggy. Just give me like 2 minutes. I'll go get something to eat. All right, cause okay, I'm back. Can you hear me? Uh, can you hear me? Can you hear me? Can you hear me? Okay. So let's talk about Universal Serial Bus or USB. Okay. All right. So USBs. Okay. USBs is okay. So we all know what a USB looks like. Okay. It's this round. It's this kind of brick that goes into your laptop. But it's not just something to store devices. Okay, that's not why we call it a USB. A USB is a form of serial transmission. Okay, I'll write this down as well. Okay, so in a USB, what happens is that okay, let me show this. So in the case of USBs, what you have is something like this. So it looks kind of like this. The old USBs, they looked something like this. And there would be like another input thingy majig. So it's mainly used for data transmission. Okay, mainly used for data transmission. Right. So in the case of USBs, there were some advantages and there were drawbacks. Okay, so that you need to know. What a USB is basically it is used to send data back and forth using one wire or serial transmission. Okay, so let's just talk about what do you say? Let's just talk about where is it? Insert table. Okay, so let's talk about the advantages and the disadvantages. Okay, advantages and disadvantages. One thing that you guys have to realize is that there isn't a lot of concept when it comes to chapter 2, chapter 3, chapter 4, chapter 5, or chapter 6, mainly because it's all memorization. Okay, it's literally just memorization. So there's not a lot of concept, but just like you need to just revise these memorizations that you're given. Okay, so USB automatically detected. I'll go over each of these. Let me just write these down. Only one-way transmission, industry standard, high speeds, no need for external power, backwards compatible, less cable length. Okay, so yeah, you can see why we use USBs. It's a pretty good thing. Okay, let's look at how a USB looks like. Okay, so if you take a USB wire, like your phone charger or anything, and you decide to be an idiot like me and you decide to cut it, what you'll see is that you'll mainly see 4 wires. Okay, let's just make 4 wires. Okay, so this wire, this wire, this wire. Okay, so these 4 wires, what happens is that one of these is the power, sorry, 2 of these is basically the power wires. Okay, so you can say what do you say, this is like the positive power and this is the negative power, and then 2 of these wires are used to transfer data. Okay, so a USB has its own power system, right? Its own way of electricity, you can say, transmitting electricity, which is basically the no need for external power points. Now whenever you plug in a USB into your computer, like for instance, if I were to plug my hard drive into my computer, it will automatically detect it. Okay, so it will automatically say that you plugged USB drive :H. You can plug in a USB and you'll see that for yourself as well. That's point 1. USBs are incredibly popular, so popular that I can probably find a random guy with a laptop on the street. I can take my hard drive to him and I can plug it into his laptop. That's how popular it is, which is why we call it the industry standard. Okay, and then it has incredibly high speeds. Okay, most of you know by now what Type-C USB is. That thing supports up to 5 gigabytes per second of transfer speed. So USB are pretty fast. Okay, they're pretty fast. Okay, and a lot of the older USB versions even, they're still supported. That's point number 6. Now, the disadvantage is that when you're working with USBs, you can't exactly make them longer than the Empire State Building, okay? They have a maximum length that they can transmit, which is usually around 5 meters, alright? You can't make it like span across the length of the Empire State Building, so it's like usually it's around 5 meters. But yeah, that's basically it about USB, okay? Yeah, that's how it's used to transmit data. Remember, it's a serial method, okay? Hence the name Universal Serial Bus, and it uses both half duplex and full duplex. All right, so that's how you it's both, and that's how basically what universal serial buses are. Okay, so yeah, Ateeb, Sohail, only advantages and disadvantages. Let me send you a picture. Why can't I upload pictures? Oh my god. Why can't I upload pictures? This is sad. Why can't I upload pictures? Can't upload pictures. Right. I'm calling out right. Right. I think he's gone. Is there any mod here? There is no mod. Okay, great. So I can ask you guys to. Okay, never mind. We're not gonna go down the road. Oh, Alu, welcome. Alu, I need a role. I can't upload pictures. I'm just blind. Okay, I can finally upload pictures. Let's go. No. Why is there a slow mode? Okay. I'm panicking. I can't upload pictures, right? I can't upload pictures. I swear I have more than 100 rep. Like, I have like 487. How? I have 487? Yo, that's crazy. Okay. That's insane. When did I have 487? I thought it was like 100 or something. Anyways, as I was saying, try now. Okay, one sec. Okay. Yeah, it works. Halo. I sent you a screenshot. That's your answer. That's the answer to your question. Okay, so that's it for the universal serial bus. Any question, guys? No question. Advantages of advantages are right here. Is there a definition? Yes, there is a definition. Okay, so universal serial bus is a form of serial data transmission that utilizes obviously serial, half duplex and full duplex. You have to make this worded better. So you can say something like USB is a form of serial data transmission that allows for half duplex and full duplex data transmission. Okay, something like that. Okay, then you have okay. So after USBs, you have my favorite thing: methods of error detection. Let's go. I love this chapter so much. I love this piece so much. Sir, can you send us notes, please? Okay. One more thing. I'm not reading any notes. This is mainly my previous knowledge and the harder book, which is on my left. I'm not using any notes right now. So, yeah. The harder book, my brain, and the syllabus. Okay. So I'm not using any notes. So you can just find notes in the thingy. I think there's cipher notes. They're pretty good. There's also pub notes for P2, but yeah, that's like the main sources for getting notes. Honestly, my best advice to you in this regard: make your own notes. Use other notes to make your own notes. Okay, if you write stuff down, you're gonna remember it more. Okay, so where am I going? Okay, so methods of error detection. Okay, so error can happen. What causes this? Causes are basically something like interference, problems during transmission, skewing. All right, so these are the three main causes for for why we need error detections, right? And why did I just get pinged again? It's too late to make notes. Oh man. Okay, so these are the main causes for error detection. Okay, so in the case of error detection, I believe we have three main things that we need to know about. We have parity checks, we have checksum, and we have echo check. Let's go over each of these one by one. Parity checks is basically okay, so each of these you can define by saying that it is a method used to check if data has been changed or not during transmission. And then you can say something like, for parity checks, you can say it counts the number of ones, okay, and determines if it's even or odd. Okay, so that's basically it. So for instance, if you have something like 11001100 and this transmitted with an even parity, okay, so you're gonna count the number of ones. Okay, so 1 2 3 4 4 ones, hence it got transferred correctly. But if you have something like 1111 1111 and it transferred with an odd parity, so these are 8 ones, which means that it was incorrectly transferred. Okay, so that's how parity checks work. Okay, besides that, okay, so besides that, the disadvantage, it's hard to conclude which bit is faulty. So like, for instance, if I send a data such as 11001100, it can also end up being something like 11000011. Okay, it can get skewed. And according to the parity check, this would be correct, even though it's not the same as the original data, which is the disadvantage of using a parity check. Okay, that's the disadvantage of using a parity check. All right. Besides this, I don't think there's much else to parity checks. There's 3D parity checks, but we're gonna get into those when we're done, when we're gonna do the past paper questions. Right now, I'm just trying to explain concept. We're gonna refer to these notes when we're doing the past paper questions. Okay. So, guys, please check out the syllabus and use it. Yeah, do that. That's a really nice strategy. What else? So I have a question. If you have a question, just ping me and ask your question. Okay. Don't say that I have a question and then not answer. Don't ask to ask. Just ask. Okay. What time will this session be until? What time is it right now? Yeah, this is definitely going till 1 or 2 o'clock. For sure. Sorry, you can just go over the recording again. We can't go back to chapter 1 and 2. Maybe at the end if we have time. Okay. Checksum. Okay. So a checksum is basically in this an extra value is added to the end of a data block. What is a data block? Okay, basically data in checksum, data is sent in blocks, right? How does checksum work? Basically in checksum in checksum data is transmitted. Okay, a checksum is calculated from the data being transmitted. Then this is used using an agreed algorithm. Okay, then this is used to transmit with the data block. So like at the end, okay, like kind of like that annoying cousin, at the end of the data block it's gonna be there. And when data is received, the checksum algorithm is rerun. If checksum same, then data transmitted correctly. Let me just give you guys an example of this. Imagine that I have a sequence of 1 1 0 0 1 1 0 0, and I say that I'm going to use an algorithm which basically says that all of the ones are counted and then sent. So like, for instance, I'm going to say that my algorithm, let's call it the Ateeb algorithm. In this algorithm, all of the ones are counted and sent at the end of the check block. So it's going to look something like this. Okay, now this is going to be received by the receiver, who's going to use this same algorithm and count the number of ones and see if the receiving data, let's just say it's the same, okay, if the receiving data has the same number of ones, okay, as the one that sent, okay. If it's the same as the checksum, then it was true. Now remember, I just use this as an example. You don't need to know. You do not, it doesn't necessarily have to be ones. It's mostly something like ISBN 13 or modulo 11, okay. It's mostly that, okay. Don't worry, you don't have to, it's not always going to be ones. I just use this as an example, okay. Don't write down that it's the calculation of ones. It's not, okay. I just use this as an example. Checksum is verifying the transmission using algorithms, okay, or this is basically the process, okay. Now lastly, you have echo check. In this, data is sent and then sent back and then verified. What does this mean? Basically, a copy is sent to the receiver. I'll explain this using a diagram first actually. So imagine that this is me and this is you, and I tell you hello. You receive hello. You send this back to me and I'm like, yes, I did say hello, and then I'm resending that hello. This is basically the echo check, kind of like an echo. I sent, you sent, I sent. So basically, in words, this would be data is sent to the recipient, data is sent back to sender. If same, then data is resent without error. Now obviously this is very slow and errors can occur while resending data, so there's a lot of reasons to not use this, okay. So any questions so far from these three methods? Do we need to know modulo 11 or ISBN 13? You do not know. How much did the team pay in IG? I did O levels, so I never really got my component marks, but my grade was A star. So do we need to know the algorithm for calculating the checksum? Not necessarily. I don't think they're gonna ask you. I haven't seen a question like that in ages, but even if hypothetically they were to ask you, they would tell you how to calculate it using a checksum. So don't worry about that, okay? You just need to know the concept. Are you sure the recording? Yeah, it's recording. Don't worry. It's been recording for the last 2 hours 37 minutes. Don't worry. I'm really surprised you got a 98. I don't even know what I got, man. My P1 was so screwed up and my P2 was so screwed up for some reason. It was a trashy paper. I don't know how I got an A star in that. Okay. So any question, guys? Any question at all? Okay. Let's move on to the next topic, which is going to be. Oh wait, I got a message. 1 sec. Okay, so the next topic is check digits. Okay, now a check digit is basically a digit included in a code that is calculated from all the other digits in the code. So if you didn't get this by now, this is basically the checksum thing. So like I told you guys, in the checksum you can use something like ISBN 13 or whatever, which basically takes a sequence of blah 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 of gibberish, uses that gibberish to calculate a number that is then sent with the data. So for instance, if you have something like I'm just gonna take an example out of the Hodder book. So you have something like 978034009 8382. Performing a checksum algorithm called ISBN 13 on this would give you a check digit of 9, which is added to the end. Now when this is received by the recipient, he basically calculates the checksum again and verifies if it's the same thing as this. So that's basically the check digit. Okay. And one more thing, in checksum, the algorithm is agreed upon by both the recipient using an agreed algorithm by both sender and recipient. So it can't be like I give you like I encrypt, I find the check digit using ISBN 13 and I expect the receiver to use modulo 11. Okay, that does not work. Okay, so it needs to be the same algorithm. Do we need to be able to explain such perform? No, you don't. You don't need to know how to perform ISBN 13. Don't worry about it. That is the biggest myth by the harder education book. Freaking weirdos. I hate those guys. I wanted to make my own textbook, but I never got the motivation to do that. I made like the first chapter and then I gave up. Okay, so any questions so far? What's the difference between checksum and check digit? I'll just explain. One sec. Okay, the checksum is a method of error detection. Check digit is basically the digit that is calculated using that algorithm in the checksum. They're part of the same strain, you can say. Why aren't you using the Cambridge textbook, the green one? It's too expensive, bro. I'm not gonna spend like 8,000 rupees on a Cambridge textbook when I have a perfectly fine 2,000 rupees black and white copy of the Hodder book. I'm not that rich, bro. Come on, who's got 8,000 to spend on a freaking book that's gonna last 3 years? When will we be studying the hardware chapter? Probably by the next hour. We're very much near the end though. Actually, probably gonna finish this chapter in like 15-20 minutes. So we're gonna do ARQs right now after these questions. There are some free versions over there. Yeah, I'm too lazy to Google it, man. I found a drive link, I opened the book and I was like, nah. Plus, I have my highlights on this book already from when I was doing IG, so that's that. Does checksum use check digit? Yes. It uses an algorithm like ISBN 13 to calculate the check digit. Alright, so, one sec. Alright, if there is no other question, let's move on to automated repeat requests. Now, honestly, this is one of the most confusing things in this topic. So, this is one of the most confusing things in this topic, so listen carefully and then I'm gonna write down. ARQ is basically, you can say it basically uses positive or negative acknowledgements, okay? So what does that mean? If I send you data and you receive it correctly, then you're gonna give me back a positive acknowledgement. If I send you data and you receive it incorrectly, you're going to give me back a negative acknowledgement, okay? Acknowledgement literally means to acknowledge something or to give your input or something or to give your review on something, okay? So it can be either positive or negative, okay? And one more thing that's used in ARQ is called a timeout. Now, let's just say I yell hello world out into the world. I'm going to say it's going to take 13 seconds to reach you. If it doesn't reach you in 13 seconds, then you're going to give me a negative acknowledgement. And you're going to be like, bro, I didn't receive it in 13 seconds. Send it to me again. Okay? These are the two main key points in ARQs. Okay? The acknowledgements and the timeouts. Now, if there is no error, a positive acknowledgement is sent back. And if there is an error, then a negative acknowledgement is sent back and data is asked to be repeated. Okay? And if there is no acknowledgement of any type within a certain time period, then a timeout is called, which is what I was talking about before, and the data is resent. Okay? And yeah, that's basically it. Let's write this down. Let's first talk about acknowledgement. Message sent to the sender, to the receiver. What? Message sent to the sender acknowledging if data has been transmitted correctly. Timeout interval, oh my god, timeout interval of the time period allowed before data is asked to be resent. Okay, so these are two concepts that you should understand. Okay, now let's talk about the different scenarios. If data is received correctly within the timeout limit, within the time interval, positive acknowledgement is sent back and all is good. Okay, if data is not received correctly, negative acknowledgement is sent back along with a request to resend the data. If no acknowledgement is sent, and time period elapses, a timeout occurs and data is resent. Alright, one more point is that if a certain number of retransmissions, meaning that data is sent back and forth, happens, then data is resent. This is mostly used by mobile networks to have data integrity. I hope ARQs you guys understand. No, I don't understand. Okay, let's use a diagram. Let's say I sent a data between this rectangle and this rectangle. I send the data. This rectangle is going to verify if the data was correct. If the data was correct, he's going to tell me a positive acknowledgement. Okay, he's going to acknowledge me that, okay, the data was correct. And it ends over there. But let's just say that data wasn't sent correctly. It's going to give me a negative acknowledgement and will ask me to send it back again. And I'll send it back again. This is the second scenario, the negative acknowledgement. Okay. Now, another scenario is that I send the data, but he doesn't tell me anything. And remember, this is all being timed. So that means that time goes on. So 1, 2, 3, 4, 5 seconds. And let's just say there is a timeout of 5 seconds. If after 5 seconds I don't receive any acknowledgement, then I automatically assume that he's dead. And I send the data again. Okay, and I cancel the request and I send the data again. That is the three things. Any IRL examples? Okay, this is perfect. Let's just say I have my cousin in front of me, and I tell him to calculate 1 plus 1. If he's able to calculate 1 plus 1 and tells me 2, that means he gave me a positive acknowledgement. If he's unable to calculate, if he just didn't get the question at all, if he's understood something like I asked 2 plus 1, then he's gonna give me a negative acknowledgement. If I tell him 1 plus 1 and he's so stupid that he can't even calculate 1 plus 1, then a timeout occurs and I'm telling him he's stupid. Okay? And then what do you say? Data is all. I automatically tell him again to calculate 1 plus 1. So that's basically the most IRL example I can give you. Any questions? What the hell? Just a sec. Okay. Ateeb, is timeout automatically detected? The timeout is, I believe, acknowledged by the sender, so the sender decides, or like the general overview of the request. Wouldn't an acknowledgement be some sort of, yeah, it would be like a confirmation sort. That's, yeah. I think after, okay. What is the lowest? That depends on the request. That depends on the request. Okay, that depends on the request. It could be anything. Timeout could be anything. It could be something like years though. Like for instance, if you're sending a message out to space, you're not going to expect it to arrive within a second. You're going to expect it to take at least years. So yeah, but the ARQ has to be used with something, right? It can't just be on its own. Yeah, I mean, neither of the checks can't be on its own. So like, you can't like checksum isn't on its own. It requires data. It requires a request. So yeah, it's not on its own. Any other questions? Okay. Just a sec. What the hell? Wait. Okay, let's ignore that for now. Okay, so hopefully you guys understood what ARQs are. Okay, let's move on to the final topic of this chapter, which is encryption. So let's oh my god. So encryption. Alright, so encryption, you have two types of encryptions. You have asymmetric, I believe that's how you spell it. And no, that's not how you spell it. Asymmetric. Come on. Yeah, that's how you spell it. And then you have symmetric. Let's just go over some basic terms. There's this thing called plain text, which is basically the data in plain form. So like if I'm saying hello, then hello is basically the plain text. Then there's a ciphertext, which is encrypted data, which basically means that if I encrypted hello to say something like hi, for instance, then hi would be the ciphertext. Okay. Then there is something called eavesdropping, which is basically like if, for instance, let's just say that I have me right over here and I have you right over here, and this is like the request. There's gonna be some lousy neighbor who's listening in, eavesdropping. So basically encryption is used to prevent eavesdropping. And the definition of encryption is that it alters data in a form that is unreadable by anyone who's listening in. So in the end, it's just gibberish to any packet sniffers. And what are packet sniffers? Packet sniffers are basically packet sniffers are basically something like somebody in a data request. Like for instance, if I'm talking to you and somebody else is listening in, they're the packet sniffers. Like if data packets are being transmitted from here to here, and there's something that's listening in and stealing them, that thing is called a packet sniffer. What else? Okay. Packet sniffers are like hackers, right? Not necessarily. It doesn't need to be a person necessarily. You can set up a server that sniffs the packets, or, I mean, sure, but like you can just like understand. You just need to define packet sniffers as like people with malware's intents who try to steal data packets and understand the conversation. I think that's what you can. Yeah. And what else? Okay, so symmetric encryption. Okay, so this is the simplest form. Uses an encryption key to encrypt and decrypt the data. So for instance, let's just say that I have a house and I have a door in that house, I have a room in that house, and this room unlocks with a key. And this room is full of Barbie dolls, okay? So what I did is I locked this room using a key. I gave that key to the recipient, and I put this thing in a truck, which is the data packets, and I sent it on its way. This is called symmetric encryption, where only one encryption key is used. Or if, for instance, you have something like Ateeb, and you say that A is equal to B, T is equal to G, E is equal to F, and B is equal to C. So you can rewrite this as B, G, F, F, C, which is absolutely gibberish. But if you note that this is equal to this, then you will know that oh, okay, maybe this means this. So like basically, if you don't have the encryption key, which is this, it's basically useless. Okay. The most common form of this encryption is called the left letter shifting encryption, which basically means if you have something like ABCD and you say like move it key is equal to move it 2 places forward, you will move each letter 2 places forward. So A becomes ABC. So A becomes like what do you say? Yeah, A becomes C, B becomes D, C becomes E, and D becomes F. So something like that. Alright, that's the most common form of symmetric encryption. Next, you have you have asymmetric encryption next, which basically involves a private key and a public key. Now, this is quite a confusing thing. Why? Because it took me a year to just understand this. Okay, so yeah. Anyways, in asymmetric encryption, you have the concept of private keys and public keys. So listen carefully. This is going to be a pretty confusing topic. In asymmetric encryption, you have like a private key and a public key. Now, basically, there are a matching pair of keys that are generated, right? So private and public key are generated using an algorithm, right? And this is basically stored on the recipient's computer. Now, the public key is sent to the sender. Okay. Now, this, what do you say? The public key. Yeah, the sender uses the public key to encrypt the data and sends the data back to the recipient, and then the recipient uses private key to unlock the data. What does this mean? It means that the public key is used to encrypt and the private key is used to decrypt. So like for instance, let's just say I want to send data from this point to this point. What happens is that this point over here creates a private and a public key. It sends that public key over to this point, and this point, basically the data that I want to send over here, it basically uses that public key to encrypt that data and it sends it over back to me, and I use my private key to decrypt that data. These keys are made in such a way that the private key can only be used to decrypt the data and the public key can only be used to encrypt the data. And that is basically what asymmetric encryption is. Any questions, guys? Packet sniffing is equal to eavesdropping. It's similar, yeah. Okay, no worries. In asymmetric encryption, you have one point and you have another point. Let's just say I want to send data from this point over to this point. Now this point over here, I want to send data right over here, right? So what's going to happen is that this point over here, which is going to be sending the data, is going to contact this point and it's going to be like, give me a private and a public key. Okay, so it's going to give me a private and a public key. Now this private key, it stays with this point. Okay, this is the receiver and this is the sender, and the public key is sent to the sender. Now the sender uses this public key to encrypt the data, which is then sent back to the recipient, and this data can only be decrypted by the private key which only the recipient has it. That's how asymmetric encryption works. So do you get it now? Okay. Basically, you have private key and a public key. The public key is sent. The public key is used to encrypt, and then that data is sent back, and only the private key can decrypt the public key. The data. That's how the both of those keys are set up. Any questions so far from this entire topic? Where you define eavesdropping? That's the same as packet sniffing, honestly. Um, yeah, I think you can just say that it's packet sniffing. It's the same thing. There's packet sniffer is in a request. Yeah. Okay. Okay, so receiver sends public key to sender, then the sender encrypts with that key and sends data. The receiver decrypts that key, the data with their, yeah, exactly like that. Packet sniffing is basically if you have one point and another point, and you're sending data packets between this. There's gonna be like an interceptor in between, and this interceptor is basically trying to copy these data packets. This is most commonly used using Bluetooth or Wi-Fi spoofing. But we're gonna learn more about this in chapter 5. Yeah. Guys, why are you arguing over KitKat? Come on. Can you explain the execute stage? We're gonna get to chapter 3 in a while. Is there any question, guys? Any question at all? Right now. Um, Oh my god, guys, just leave it be. There's gonna be no point. There's no point of arguing on text. Like, come on, what is this? It's just a bunch of request data packets. Come on, do data packets really matter to you that much? Chill out. Any question, guys? Okay, with this we can conclude chapter 2. And okay, can't the eavesdropper get the public key? The public key can only be used to encrypt the data. It cannot be used to decrypt the data. The public key and private key are generated in a way that the public key is used to encrypt data and the private key is used to decrypt that data. So sure, it can get the public key, but it will be of no use to him. So yeah, let's end chapter 2 right over there, and let's take a 10-minute break again. Packet sniffers examine. Packet sniffers are used to sniff packets. So like that, the packets can include like the IP address, the payload, and stuff like that. So yeah, their definition is partly correct. So yeah, guys. Is there anything else? Packet sniffers are used to sniff packets. Okay, then we're gonna conclude chapter 2 over there, and yeah, I'll see you guys after a 10-minute break. I'll be here at at exactly 07. Lewis Hamilton. Lewis Hamilton. Lewis Hamilton. Oh, that shit's cursed, bro. That shit's cursed. Okay. Anyways. Still got 7 minutes. What was I gonna do? Oh, we're at 3 hours officially. That's very little. Can you go through capacity? Yeah, we will in chapter 3. We're gonna start chapter 3 in exactly 7 minutes. Don't people in Punjab sleep at 9? For the last 7-8 days, I've been sleeping at 9 a.m. and waking up at, I don't know, like 13 o'clock. Yeah. So, yeah, I do sleep at 9, just like in the morning. Chapter 3 just pissed me off. Honestly, if you understand how stuff works, chapter 3 is gonna be the easiest chapter you're gonna do. Genuinely. Like, if you understand what each component does, then it's gonna be the easiest thing. You know what? I'll even make it fun for you guys. I'm gonna bring out my actual collection of sensors just to show you guys how it actually is like, if I can find it. You know what? I'll go find that shit. Hold on. Wait, is embedded systems part of chapter... Wait, are sensors part of chapter 3 or chapter... I'm confused. Wait, hold on. Sensors. Oh, they're part of chapter 3. Okay. Kind of part of chapter 3 along with chapter 6. Okay, easy peasy. Okay, I'll save the sensors for chapter 6. I'll save the sensors for chapter 6. Embedded systems. I'm going to explain the entire thing. I'll explain the entire thing with embedded systems. I thought my exams are gonna come back online, but it looks like they're gonna get delayed again, bro. What the fuck? Sir, can you bring me to the stage? What are you gonna do on stage? What are you gonna do on the stage, bro? He's gonna dance. You wanna say something? Is that something gonna be against the rules of the server? I'll show the notes. I'll put the notes on screen. Is that something gonna be against the rules of the server, my guy? No? Is that gonna be anything against KitKat? Oh my god, who the hell sent the wall text, bro? Run! Is that something gonna be against KitKat? You wanna make an apology? Rad, can you please give Paulo like speaker, please, pretty please, like for 2 minutes. I just wanna see what this guy has to say. I'm curious. Plus we got like 4 minutes. Just know I warned you, Ateeb. Oh, how funny would it be if I bring him and KitKat on the stage? Oh shit. Oh my god, who's sending the wall text, bro? Chaos for 3 minutes, alright. KitKat, you send a request as well. Right, if these two like send you a request, then just like accept them, please. Thank you. Hey, Paulo.
Yo, KitKat.
Can
Is he still here?
wait? Hold up. Is KitKat here?
KitKat?
Is
Is he still here?
Is he?
Is he still here? I'm sorry, KitKat. I'm sorry.
He's apologizing. Where's KitKat, bro? KitKat, are you here? No, wait, he's gone. Is he gone? I don't see him in the thingy. Shit. Oh man, he left.
Bro, why are you swearing? We're your teacher. Why are you swearing?
Oh man. Public apology.
People these days.
Oh, who is this?
Yo. Hello?
Hey,
Hello?
who are you, my guy?
I am the cousin that Ateeb gets compared to.
Oh shit. Oh, I have a lot to say against you then.
Bro, go on. My name is Tung 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 Sahur.
Oh, KitKat's here. KitKat's here.
This is not KitKat. This is not KitKat.
This is a KitKat. It's some kind of a KitKat.
It's a big KitKat. It's fake KitKat.
Pretend it's the
KitKat is a
real.
dog.
Pretend it's the real KitKat. Pretend it's a real KitKat.
Okay. KitKat. Fuck you, nigga.
Oh
Yo,
fuck.
yo.
No.
Yo.
That was a bad idea.
No, I don't
Okay.
think
We're done with speakers. Let's do chapter 3. We're done with speakers. We're done with speakers. That was a bad idea. Oh shit. Oh man. Okay, that was. Okay. Anyways, just another minute. Okay. This is like kind of like the what do you call it? The halftime show at a Super Bowl. Feels like it, man. Like. Oh man. Somebody tell KitKat his arch nemesis just got timed out, bro. He's gonna be so happy. Okay. Okay, we're gonna start chapter 3 in 1 minute. Yes, this is being recorded, don't worry. Alright, let's do chapter 3. Where's my book at? Let me just create a new file. Okay, let's do this. Let's do chapter 3. Okay. Where will I be able to watch the recording? I have no clue. I'm gonna decide afterwards if it's gonna be like on a Google Drive or on a YouTube channel. I'll figure it out afterwards. I need to edit I need to edit it as well because I forgot to mute OBS in between, so there's like noise. So I'll upload it probably by tonight, hopefully. Is the Kit Kat Paulo part gonna be? Of course. Why would I cut out insane lore, man? Come on. The people who are watching this in the future, in October, November, or February, March, they need to know what it was like. All right. So there, know the propaganda, man. I think that would be the reason that people click on those videos. All right, bet, right? You know, you need to add it in the headline of the YouTube video. Paulo versus Kit Kat. That's crazy. Okay, so let's move on to chapter 3. So, in a computer, you have the central processing unit, or the CPU, right? This basically contains it's basically a very small circuit. It's a small circuit slash chip. Okay, it contains of different components which are part of our system, which are basically the ALU, arithmetic logical unit. Oh no, sorry, arithmetic and logical unit, and the control unit, CU, control unit, different buses and registers. These are the things that it comprises of. Okay, so what else? Okay, so when you're talking about a CPU, there's the very old von Neumann architecture. There was this very old guy called von Neumann. He went by the name of von Neumann. He's dead now, I'm pretty sure. But he basically set up this entire system of computers that uses different buses. Okay, and it basically uses these different components that are part of our CPU. Okay, and these components, basically, let's talk a bit about these components. In our syllabus, there is the let's just make a table of these components. Okay, component name and description. Alright, so the first component in this architecture is the arithmetic logic unit, ALU, the control unit, CU, the registers. Alright, let's just write registers, and then let's do the current instruction register. I'll go over each of these. CIR, the accumulator, ACC, the memory address register, MAR, memory data register, MDR, the program counter, PC, the different buses, the data bus, the address bus, and then the control bus. So these are like the main components that you need to understand this topic, to get a good grasp on this topic. Okay, so let's first look at the von Neumann architecture system. Okay, I'll go over here and I'll explain how the von Neumann architecture system works. Okay, so let me just roll out an image of it. Von Neumann architecture. Let me just pull out a really simplified image. I have no clue where to find this. Let me just. Okay, we're gonna make our own diagram. It's fine. We're gonna make our own diagram. Okay, so the von Neumann architecture system, let me just explain what it looks like. So there's the CPU, we call this the CPU. Basically, this is also the fetch, decode, and execute cycle. I'm going to explain this whole thing in one go. Okay, so you guys better listen. I'm going to explain the entire thing in one go. Alright, so in the von Neumann architecture, what happens is that, let me just bring out my pen. Okay, in the von Neumann architecture, you have the program counter. Okay, you have the program counter. I'm gonna use abbreviation, so don't get confused. All right. Then you have the MAR. You have the MAR. Then you have the control unit, the CU. Then you have the who is pinging me? Okay. Then you have the ALU. Let's make ALU down here, and let's add a small accumulator down here as well. Then that's the CIR, the MDR. Then you have or let's memory. This is the RAM. Alright, so let me just explain what happens in the fetch, decode, execute cycle, or the von Neumann architecture. So it's pretty simple. The first thing that happens is that what do you say? Sorry. My bad. I lagged out. My bad. Okay, so the what was the last thing I said? What was the last thing I said? I lagged out. something Kit Kat. No. I think I was okay. I'll just go over it again. Okay, so the first thing that happens is that the program counter, okay, the PC, it basically has this address. A thing that you need to know is that inside of memory, inside of RAM, there's a bunch of data. Each data is referenced to by an address. Okay, so for instance, if you have something like this, and you have a bunch of numbers like 1, 2, 3, 4, 5, each of these numbers, which are our data, have a different address to it. So it could be 0, 1, 2, 3, 4, and so forth. Okay, so each data has a different address to it. Okay, a unique address. Now what happens is that the program counter, basically in a fetch, decode, execute cycle, the program counter basically has the current instruction that should be run. Okay, the program counter has the instruction that should be run. Okay, the next instruction, right? What happens is that this instruction is copied to the memory address register. Okay, this is the first step. It's copied to the memory address register, and it's copied using the address bus because it's an address. Okay, remember that. Now the next thing that happens is that the MAR is basically the contents. Basically the MAR sends this address to the RAM and finds the data that is corresponding with it. So like for instance, if the PC had the address 1, it got copied to the MAR, and then the MAR used this address. So like this is the address and this is the data. So the MAR used this address to find the data, which was 1, and it basically got this data and then it sent it back. Okay, it sent this data back to the MDR right over here. Okay, using the data bus. Do you guys get what it just did? right now to this point? Do you guys get what happened to this point? I'll send you a diagram as well, don't worry about it. But basically this is what happens so far. Now this data is then copied to the CIR as well, okay, the current instruction register. All right, just a sec. Sorry, yeah, this address is also stored in the current instruction register, okay. And what happens next is that what happens next is that the value in the program counter, it's incremented by 1. So for instance, it was 1 before, then it becomes 2, and then it will become 3 after the next instruction, and so on. Now this is the fetch cycle, okay. Now the decode and execute. What is decoding and executing? The data in this thingy is sent to the ALU, where it performs operations and uses ACC as a small storage, okay. And then this whole calculation is performed, and then the result of this calculation is sent to the control unit. And then this is sent to the control unit, and I think I'm screwing up somewhere. Just give me a sec, guys. I think I messed up somewhere. No, I did not. Okay, yeah. And then the control unit sends out signals to the rest of the computer in the form of control signals or control buses. Okay, so it's a pretty confusing topic, yes, but I'll try to explain it better as we go. So let's first discuss what each of the things are. The arithmetic and logic unit. Okay, let's talk about the ALU first. ALU is basically a component that performs the required arithmetic tasks or logical tasks. What does this mean? The arithmetic tasks are basically mathematical operations, so plus, minus, divide, multiply, and so on. These are the I'll explain, don't worry. So these are the arithmetic operations, okay, so plus, minus, etc. Okay, so then and the logical operations are basically or, and and or, okay. So these are the tasks that are being performed by the ALU, okay. That is what the ALU does. It performs arithmetic and logical tasks, okay. Now the control unit is basically it's used to read an instruction from the memory, okay. This is okay. Oh, one sec. Sorry. It's used to read an instruction from the memory. Now the registers, okay, so these two definitions right now you need to what do you say, you should know these definitions, okay. So then you have the program counter. Let's talk about the program counter. This stores the address of the current instruction, okay. What else? Okay, so then what happens is what else do you got? You have the memory address register, stores the address as given by the program counter. Then you have the memory data register, stores the data received from the RAM, from the memory at the current address. I'll go over each of these one by one, okay, so don't worry right now. Okay, don't worry right now. The CIR stores the current instruction that's being executed and decoded, used as data storage while performing calculations. Then you have the data buses. The data bus used to transfer data from memory to MDR, used to transfer address from memory, used to find address in memory from MAR, and used to send control signals throughout the component. Okay, so it might seem a bit confusing right now, but okay, let me explain. The fetch, decode, execute cycle. Now these are all the registers, okay. You should know what each register, each component of the CPU does. Okay, you should know all of this. Okay, it's just my own wording, but you should generally know what all of this does. Now, what happens is that the fetch, decode, execute cycle. Okay, let's do this. Fetch, decode, execute cycle. This can be divided into three portions: the fetch portion, the decode portion, and the execute portion. Execute. Okay, so the fetch portion. Okay, the fetch portion. What happens is that the program counter stores the address of the next instruction to be run. Okay, so it stores the address, like for instance 1, 2, 3, 4, whatever the address is, of the next instruction, the one that should be run. Okay, now what happens now is that this address, the address from the program counter, is copied to the MAR. Okay, the address from PC is copied to MAR. Okay, then you have using the address bus, then the contents, okay, the contents at MAR are used to the contents in memory at the register, at the address in the MAR, are copied to the MDR using the data bus. What does this mean? This means that the contents, the MAR, it stores the register, like 2, 3, 4, whatever the address is. This address is then located in the RAM, in the memory. The data at that address is then sent back to the CPU into the MDR. That's basically what this means. Okay, using the data bus. Then what happens is that the the instruction address is copied to the to the CIR, which is the current instruction register. And then what happens is that the program counter is incremented by 1. Why does this happen? So that we can move on to the next instruction. Okay, so that we can move on to the next instruction. That's what, but this is basically the fetch part. Any confusion in the fetch part of the cycle? Any confusion in the fetch part of the cycle? Just the fetch part for now. Okay, I'm gonna assume that there is no okay, the first step is that the program counter instruction is copied to the MAR. All right, the MAR, the instruction at MAR, the instruction address at MAR, the address that is stored in MAR. Okay, this address is co-referenced with the data in the memory. Okay, so like for instance, if there's the data called Ateeb at the address 3 and the address is 3, the data Ateeb is fetched using the data bus to the MDR, which is the memory data register, and the address is also copied to the current instruction register, the CIR. Then what happens is that the program counter is incremented by 1 to move on to the next instruction. So like if it was 2 before, it will become 3. That's basically the fetch cycle. Any questions? The address is fetched from the program counter and copied to the MAR. Increment means to add. So like if I say the program counter increments by 1, if the program counter was 3 and it increments by 1, then it becomes 4. Could you explain MDR, please? Is the data copied from MDR to CIR? CIR is an instruction register. It stores the currently running instruction that will be decoded. What is the next topic? Okay, wait, hold on. Could you re-explain MDR? So the data, the address in the MAR, okay, the MAR holds the address. This address is referenced to the memory. Okay, so the memory, the address at the memory. So like for instance, let's just say the MAR theoretically holds the address of 4. Yeah, let's just say I have this RAM right over here. Okay, let's just say I have the RAM 1, 2, 3, 4. This is the address, and let's just say I have a bunch of numbers. So like 300. 400, 500, 699. Alright, so I have the address and then I have the data. Let's just assume this is my RAM. Okay, so the MAR has, let's just say the program counter has an instruction of 1. this instruction is copied over to the MAR. Now the MAR has the address of 1 as well. So what the MAR does is, using the address bus, it fetches the data in the RAM, so like the 300, and it stores this data into the MDR. So now the MDR holds the data 300 using the data bus. Okay, that's the role of the 300. Now what happens is that the CIR also stores the currently running instruction, which is 1. And then what happens is that this program counter, the loop restarts, and this program counter increments by 1, so it's now 2. And then that 2 is copied to the MAR, and then the 2 reference data, and then this is fetched, and 400 becomes, and then this stores 2, and then this becomes 3, and then 4, and then so on. That's how the fetch execute cycle works. The fetch cycle works. Any questions? Alright, great. Now the second part is called the decode part. Now it fetches a number or whatever. It fetches a number. I'll reference this by steps. Okay, no worries. 1, 2, 3, 4, 5. Okay. Now the next thing that happens is that it fetches the thingy, right? It fetches the It fetches the data. Now what does it do with the data? It basically uses the arithmetic logical unit, the ALU, uses the ALU to perform arithmetic and logical operations. The ALU uses the accumulator to store data, to store temporary data. What does this mean? Now, for instance, let's realistically, a RAM won't have random numbers. A RAM will have like different instructions to be carried out, right? So what you want to do is that so basically in the decode stage, the instruction is copied to, okay, so in the ALU what happens is that the the instruction that we just received from the memory, that instruction in the ALU, it's run. Okay, so if it's a logical operation, that logical operation is performed. If it's an arithmetic, that arithmetic operation is performed. And doing all of this, if there's any temporary storage that's required, the accumulator is used. So for instance, let's just assume that these 300s, 400s, 500s, whatever the hell they were, these were the instructions that to be performed. So after they fetch the instruction, the data that is required, what happens is that this data and the instruction is sent to the ALU, okay, and the ALU has a small component inside of it which is called the ACC. The ALU basically decodes this instruction and runs whatever the hell it needs to, and uses the accumulator as kind of like a small buddy to perform those calculations. And then this whole sequence, this instruction is sent out. This is the decode stage, okay, uses the arithmetic logical unit. Any questions about the decode stage? Just these 2 points for the decode stage. Okay, I'm gonna guess there is no is there any questions for the decode stage? Am I lagging? Okay. Yes, it's basically storage for accumulator. It's basically storage for the ALU. Okay. So, lastly, you have the execute stage. Now, the ALU, it decodes the instruction, and then it sends it to the control unit, sends out control signals using the control bus to different components to do those tasks. So, in reality, what happens is that the program counter has an address. It copies this address to the MAR. The MAR finds the address, and then it gets the data and the instruction. Okay, remember the RAM contains the data and the instruction. Okay, we call this an instruction set. I'll come back to that in a while. It sends this over to the MDR. Now the MDR has the data and the CIR has the instruction, right? And then it uses these two things to calculate using the ALU, and then the ALU performs this calculation, and the control unit uses this calculation to send out signals to the rest of the computer. Alright, that's how the fetch, decode, execute cycle works. Did you guys get what I said? MDR and CIR are placeholders. Yeah, you can think that they're just placeholders, that they have their own role, of course, but they're used to store the instruction set. After ALU, what happens? The control unit uses that calculation to perform tasks all over the computer. So it sends out control signals or signals to the rest of the computers. What is the fetch decode? We'll get that in a second. Right now, you need to understand what it actually is. So do you guys understand what it is? Any questions about the fetch, decode, execute cycle till now? What's the difference between actually? We're not at that point yet. Not at the point yet. Alright, so if there's no question, let's move on from the fetch, decode, execute cycle. What else do we have? One sec. Okay, 1 second. Somebody. Okay, so then we have a few key terms. Okay, these key terms are what do you say? These key terms are cores, caches, and the internal clock. Now the core is basically the number of cores in the CPU. So like for instance, if you have an Intel Core i5, I believe it has like 5 cores or something like that. It's something along the namings, right? It's something like that. But no, sorry. If you have a 4-core processor, that's going to be faster than a 2-core processor. If you have a something like that. Oh my god. Give me a second. Let me just drink water. I'm speaking gibberish right now. Okay. So, the cores, the clock, and all of this. Okay, so there's this thing that we call the clock speed. Okay, let's talk about clock speed. Clock speed, usually, you know, this is like in the form of gigahertz, megahertz, stuff like that. So like for instance, you can say that I have a 3 gigahertz processor or 4 gigahertz processor, so on and so forth, right? Now the system clock basically is the it basically defines the clock cycle that synchronizes all computer operations. Okay, so for instance, something like 3 gigahertz could mean that there is 3 billion clock cycles a second, right? So the clock speed is basically used to measure the overall performance of a CPU. Okay, so then you have the cores, right? So there's a few factors that we need to take into account that can affect the clock speed, right? So these are namely the let's just delete this for now. These are the width of the buses. So like for instance, if the address bus has a greater width or the data bus has a greater width, then more faster clock speed, right? Because like if it has a greater width, then that means that it can perform more of those data transmission tasks. It can transfer more larger addresses, more data, and so on, right? That's basic knowledge. If you have a wider bus, then that means that you can perform more clock operations a second. Next, you have the overclocking. Overclocking basically means to get into the BIOS of a computer and changing the setting so that the clock speed increases. Now we've all done some kind of overclocking, you know, when playing games or stuff. So you can actually increase your clock speed by pushing the CPU to its limits. Though again, the disadvantage with this is that if you do this, then that means that you're damaging the CPU in the long-term memory, since you're overheating it. Okay, That's overclocking. All right. So then you have okay. Then you have cache. CPU has a cache inside of it. Okay. Now this is incredibly fast to reach. So like if the CPU uses some storage to store information, right? To store any kind of information, that's called the cache. And this storage inside of the CPU, it's super fast. Okay, you can access this almost instantly. Okay, it's incredibly fast. This is called the cache. It's usually very, very small. All right, and obviously the more it is, the faster the performance. All right. Then you have the number of cores. Right. The number of cores, basically, one core is made up of an ALU, CU, and the registers. So obviously, if you have more cores, that would mean more performance, right? So, but however, if you double the cores, that doesn't necessarily mean you're doubling the clock speed. The reason for this is, imagine that you have two cores. Now remember, these two cores need to communicate with each other as well. So if you double the amount of cores, if you have two cores, that doesn't mean you're having 2 times the performance as you would with a single core, since you need to make those cores communicate with each other as well. Okay, and okay, and yeah, that's it. Okay, now let's do the last thing, which is second. Sorry, not the last thing. Let's do instruction sets now. Instruction sets. Instruction sets are basically contain an operand and an opcode. In A levels, you'll realize it's gonna be something like add to or inc 3 or LDCL IX something. It's something like this. Okay, so the first part, the letter part, is basically called the opcode, and the second part is called the operand, I believe. Yeah. So this is the opcode is basically the instruction that should be done, the operation, and the operand is basically the value. Okay, the operand is basically the data. So you should know opcode is basically for the command to be run, the operation to be run by the CPU, and the operand is basically the data used to perform the operation above, right? So that's basically it. The instruction set, okay, an example of the instruction set is the x86 instruction set. You just memorize this, you don't need to know much about it. Example, you may have seen that a lot of your CPUs, either an x86 processor or an x64 processor, but yeah, there's also like ARM based thingies, but yeah, this is like what an example instruction set looks like. ADD2 or something like LDA #3, something like that. So that's what an instruction set looks like. Okay, that's what an instruction set looks like. Okay, any questions so far? What does 1 gigahertz mean? Does it mean 1 billion instructions? 1 gigahertz means 1 billion instructions done per second. Is 1 clock cycle 1 FDE cycle? Yes, it is. If cache is too big, wouldn't it slow down as well? Because again, they're not quite literally linearly proposed. Like I said about clock speed, like I said about the number of cores. Sorry, if you have 2 cores, then that means that if you have 2 cores, that doesn't necessarily mean that you're gonna have 2 times the speed, which is the disadvantage. The more cores you have, the more you're gonna. Okay, I'll explain this entire thing again. Clock speed is basically used to reference how fast a computer processor is. Okay, and there's a bit of different factors that basically tell us about it, which are the address bus, the overclocking, the cache, and the number of cores. These are the four factors that can affect the clock speed. The width of the buses, the wider the buses are, the more data you can say they can transmit. So hence, if you increase the width of the buses, then that means that you'll have a faster clock speed. Then you have overclocking. Now you can get into the BIOS of your computer and you can make it so that the CPU overheats and performs more FDE cycles every second. We call this process overclocking. Now overclocking has a disadvantage as well, which is that it causes the CPU to overheat and can lead to long-term issues. So it can reduce the life of your CPU long term. That's the disadvantage of overclocking. Then you have cache. The cache is basically a temporary storage inside of a CPU. This is like very easily accessed since it's like right inside of the CPU, so you can easily access this. Plus, it's really fast to access. So if you have a lot of cache, that means that the performance will be faster since you can store more data. Then you have the number of cores. The number of cores is basically the amount of ALUs, CUs, registers, basically the amount of von Neumann architecture thingies that you can store inside of a CPU. And the more cores you have, the faster the performance. However, the disadvantage is that the more cores you have, the more they need to communicate with each other. Alright? So if you have 4 cores, that doesn't necessarily mean that you're quadrupling the performance, because those 4 cores also need to communicate with each other. Alright? So that is basically the clock speed. Any question? Is instruction set used in the ALU part? That is wait, hold on. Is an instruction set used in the, what do you mean? Yeah, you'll get this file after, don't worry. No, not in the decode cycle. No. The decode is just a ALU which uses the data from the CIR and the MDR. Okay. The control unit basically, listen. The control unit uses instructions from the instruction set to trigger actions, okay? The control unit uses the instruction set, but it doesn't like directly write instructions to the MD or the CIR, okay? If that makes sense. The CIR basically stores the current instruction being executed, and the MDR uses the data that is going to be used for that. The control unit uses the instruction set to carry out the instruction that needs to be executed. Hope that makes sense. Any other questions? This is chapter 3, yes. Would you outline the entire FDE life cycle in SMS? This is like, okay, the one sec, my MacBook is lagging. To be honest, we might need to end this session right now and start one tomorrow early. The rest of the chapters aren't linked to the FDE, and chapter 5 and 6 can be merged. So tomorrow probably around the same time, so like I'd say like around 18 o'clock Pakistani time. Okay, so let me just sum up FDE cycle, and I think we might need to end it over here. At the FDE cycle, we'll start from embedded systems and the remaining chapter 4 and 5, 6 tomorrow. 6 p.m. Not 8 p.m. Not 8 p.m. 6 p.m. Okay, so yeah, okay. let's just go over the FDE cycle one last time and end the session for today. Okay. So in the FDE cycle, I'll try to upload this by tonight, and I'll like send a link in the our IGCSE thing. I need to edit the recording first, so yeah. So as I was saying, in the what is it? Okay, so in the fetch decode execute cycle, what happens is that the first step is that the program counter basically stores the address of the next instruction to be run. Okay, now this address is copied over to the MAR using the address bus. Okay, and then this address bus, then the MAR basically finds the data, and the instruction to be run using the memory, which is the RAM, right? So it fetches the data from the RAM. Okay, and it stores this in the MDR, and the CIR basically contains the current instruction. Okay, the current instruction that needs to be run. Now the ALU uses these things to come up with the calculation that is then run by the control unit to send signals across the entire computer, right, to different parts on the motherboard, you can say. Now at the very end, the program the program counter increments by 1. That's it. Oh, one more thing. Let me go over one more definition that you should know. The definition is the definition of the system clock. Which is basically the system clock basically produces timing signals on the CU to ensure synchronization takes place. So basically, it ensures that another instruction is not run before the previous instruction is finished and stuff like that. So I'll send a timestamp. Hold on. I'll send a timestamp. Timestamp. I can't tell you guys for sure. It depends on what time I wake up at, but I'll try to do it early so that we have more people as well. So let me just get the timestamp for you guys. What time is it? It's almost 12. Nice. Okay. Let me just get the timestamp for you guys. It's 1:49 a.m. It's 1:49 a.m. Damn. I'll just send the timestamp in the chat right now. But yeah, I think we can conclude this ad right now. I'll upload the recording and I'll upload the 3 notes. And we will pick up from this point tomorrow. Let me just get the timestamp. And yeah, okay, fun stuff. Let's rate accounting. Is there an accounting session going on? There is no accounting session going on. Is there an accounting session going on? I can't tell. Where is the accounting session? Oh no, not on Zoom. Come on, it needs to be in the Discord now. We're not gonna rate some poor guy's accounting session on another platform. And if it was in the server, I'd be like, yeah, sure, bet, why not? Discord timestamp 3v.fi. Okay, let me just generate one. Are you done for today? Yeah, we're done for today. Guys. We're done for today. I'll just generate the timestamp and I'll send it in the chat right now. 11:18:00. Okay, so this should be it. Okay, so this is the time. Around this time, I'll make the session maybe like 30 minutes before or 30 minutes after, but we'll pick up from this point tomorrow. Okay, and yeah, I think that is it for today. 11 p.m. Oh man, I'll try to do it earlier. I'll try to do it like an hour before. So yeah, I'll try to do it an hour before, an hour or two before. So just expect me to do it like I'll get Rud to message like 30 minutes before I do the session in the study session channel. Okay, where are you uploading the notes right now? I'm gonna edit the recording first of all, and then I'm gonna upload the recording to a Google Drive, and I'll just send that message in the IGCSE Computer Science thing channel. All right. So thank you guys very much for your time, and yeah, I think words of motivation for the exam tomorrow. I'll give you guys all the words of motivation. Don't worry. Tomorrow. I'll give you guys tips and everything. All right. Tomorrow. So yeah, I think that should be everything. Yeah, and if you guys don't have any questions, let's end the session here, and we will pick it up from tomorrow. I'll tag everyone. I have no clue if I can tag everyone. I'll just send the message. So like, just expect it like in the next 2 hours to be uploaded. Depends on my Wi-Fi, right? Or 5 reps away, bro. We're 5 reps away from 500. We're 5 reps away from 500. Holy shit. Okay. We're gonna reach 500. We're gonna reach 500. Took me 2 years. No, a whole year, yeah. We're at 500. Fuck yeah. Oh man, thank you guys so much. Thank you guys so much. Alright. I'll see you guys tomorrow. And yeah. Oh, where the fuck is the helper app? I need the helper app. Helper app. Okay. Alright, I'll see you guys tomorrow. Have a nice rest of your day. And goodbye, guys. Peace out. And time to stop the recording.